Good morning, all of you. Today I'm going to make an audio recording for visual impaired students of Organic Chemistry book of Dr. J.M. Segal. Modern book. Name of the chapter is Stereochemistry of Organic Compounds. 2.1 Introduction. The molar structure of compounds play a very important role in the study of organic chemistry. During the study, one comes across many instances where a given molecular formula represents two or more compounds having different properties. This is evidently due to some difference in the molar structures of these compounds. Such compounds will have the same molecular formula but different properties are known as isomers, and the phenomena is known as isomerism. 2.2 Isomerism. The concept of isomerism is an important feature of the study of organic compounds. It's related to the existence of different compounds which have the same molecular formula but different properties. Such compounds are called isomerism. Iso is equal to same, mers is equal to parts. The difference in the properties of isomerism is due to the difference in the relative arrangement of atoms in their molecules. There are two types of isomerism. First is structural isomerism, second, space or stereoisomerism. 2.3 Structural isomerism. This is the type of isomerism which is due to the difference in the arrangement of atoms within the molecules having the same molecular formula. The student is already familiar with the various types of structural isomers. However, we shall present here a brief review for the sake of recapitulation. First, chain or nuclear isomerism. This is a kind of isomerism which rise when the compounds having the same molecular formula differ only in the arrangement of carbon atoms in a chain. Thus, normal butane and isobutane having the same molecular formula C4H10 represents two chain isomerisms. CH3, CH2, CH2, CH3 and butane. CH3, CH3 on second position CH3 isobutane. Similarly, there are three chain isomers having the molecular formula C5H14, C5H12, CH3, CH2, 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 CH3 and pentane. CH3, CH, CH2, CH3 on second position CH3 isopentane. CH3C, CH3 on second position 2 methyl group CH3, CH3 neopentane. Second, position isomerism. If two or more compounds with the same molecular formula having different positions occupied by a characteristic atom or group attached to carbon, position isomerism is said to exist. N-propyl chloride and isopropyl chloride afford an outstanding example of this type of isomerism. Both these compounds have the same molecular formula C3H7Cl, the same carbon skeleton but different from each other in the position of attachment of chlorine atom. CH3, CH2, CH2Cl and propyl chloride. CH3CHCl, CH3 isopropyl chloride. Similarly, there are two butenes C4H8 which differ in the position of double bond in the molecule. CH3, CH2, CH2 but 1 in. CH3, CH double bond CH single bond CH3 but 2 in. Third, functional isomerism. This type of isomerism is due to the presence of different functional groups in compounds having the same molecular formula. For instance, C2H6O represents two compounds CH3CH2OH ethyl alcohol, CH3OCH3 dimethyl ether. These two compounds have entirely different physical and chemical properties because of the presence of different characteristics groups. Acetone and propionaldehyde C3H6O represents another pair of compounds exhibiting functional isomerism. CH3CO, CH3 acetone, CH3, CH2, CHO, propionaldehyde. Fourth, metamerism. This type of isomerism is due to the difference in the distribution of carbon atoms on either side of functional group in compounds having the same molecular formula. For instance, dimethyl ether and methyl propyl ether represent a pair of metamers having the molecular formula C4H10O. CH3, CH2O, CH2, CH3, diethyl ether. CH3O, CH2, CH2, CH3, methyl propyl ether. Diethyl ketone and methyl propyl ketone having the molecular formula C5H10O furnish another case of metamerism. CH3, CH2, CO, CH2, CH3, diethyl ketone. CH3CO, CH2, CH2, CH3, methyl propyl ketone. Fifth, ring chain isomerism. This is the type of isomerism in which two compounds having the same molecular formula has open chain and ring structures respectively. For example, propene and cyclopropene having the molecular formula C3H6 afford a single example of ring chain isomerism. CH3CH double bond CH2 propene, CH2CH2CH2 cyclopropene. Similarly, but1-ine and cyclobutene are also ring chain isomerisms of each other. CH3, CH2, C triple bond CH but1-ine cyclobutene. 6. Tautomerism. This is a special type of functional group where the isomers exist simultaneously in dynamic equilibrium with each other. The isomers which are involved in equilibrium are called tautomers. The structure of tautomers generally differ from each other in the point of attachment of one of the atom in the molecule. In keto-enol tautomerism, which is the most important type of tautomerism, the tautomers differ from each other in the point of attachment of a hydrogen. Thus, ethyl acetone exists as a tautomer mixture of two forms, the keto form and the enol form, which differ in the point of attachment of a hydrogen as shown below. CH3CO, CH2CO, CH3 keto form of acetylene acetone. CH3COH double bond CHCO CH3 enolic form of acetyl acetone. Similarly, ethyl acetoacetate exists as a mixture of keto and enolic form. CH3CO, CH2CO, OC2H5 keto form. CH3COH double bond CHCO OC2H5 enolic form. Tautomerism versus resonance. It will be quite appropriate at this stage to distinguish between the phenomena of tautomerism and resonance. It may be noted that first, tautomerism is marked by the existence of distinct structures which differ mainly in the point of attachment of one atom in the molecule. On the other hand, in case of resonance, the different contributing structures having the same arrangement of atoms. Second, the tautomers are distinct compounds which are actually known to exist and which may even be isolated in certain cases. On the other hand, in resonance, contributing structures do not exist as such. They are written only to have an idea of the structure of resonance hybrid. As this structure cannot be represented in terms of the valence bond method of representation. 2.4 Stereoisomerism. This is the type of isomerism which arises due to the difference in the arrangement of atom in space. Its study is known as stereochemistry. In this unit, we shall discuss the important aspects of stereoisomerism. Stereoisomerism, the isomeric compounds which differ from each other only in the relative arrangement of atoms in space but resemble one another with respect to which atoms are linked to which other atoms are called stereoisomers, and the phenomena is known as stereoisomerism. There are three types of stereoisomerism. First, optical isomerism. Second, geometrical isomerism. Third, conformational isomerism. Before proceeding further, it may be pointed out that the different structures of conformational isomers of a substance are non superimposable on one another but are easily interconverted in each other by rotation around single bonds. In contrast to this, the different structures of optical or geometrical isomers are non superimposable on one another, and at the same time they cannot be interconverted except by breaking and making of bonds. For this reason, optical and geometrical isomers are also collectively known as configurational isomers. While conformational isomers of a substance exist only as a mixture of different forms, the configurational isomers can be prepared as distinct individual substances. For difference between conformation and configuration, please refer to Sec 2.20. We shall now discuss the different types of stereoisomers, starting with optical isomerism. 2.5 Optical isomerism. This is a type of stereoisomerism in which the isomeric compounds resemble one another in their chemical reactions and most of the physical properties but differ in their effect on polarized light. We shall now first review some fundamental terms concerning optical isomerism and then discuss other features of optical isomerism. 2.5.1 Tetrahedral concept of carbon. It is well known that in methane and all other compounds having a carbon bonded to four other atoms or grouped by single bonds, the four bonds of carbon are directly towards the four corners of a tetrahedron. The tetrahedral concept of carbon put forward by Liebel and Vansoff is very helpful in understanding the phenomena of optical isomers. A representation of tetrahedral carbon atom is shown in figure 2.1a by molecular model and in figure 2.1b by Watt's formula. A molecular model B. Wedge projection. Representation of tetrahedral carbon. It should be noted that by convention the wedge representation, the bond pointing towards the observer out of the plane of the paper, the hatched line or dashed line represent the bond behind the plane of the paper. The normal lines show the bond in the plane of the paper. 2.5.2 Polarized light. An ordinary ray of light consists of electromagnetic waves of various wavelength, and its vibration take place in all planes at right angle to the direction in which it travels. A ray of light which consists of wave having only one wavelength is known as monochromatic light. Even such a ray has its vibration in all planes. However, if a ray of monochromatic light, such as yellow light from a sodium flame, is passed through a nickel prism, a special prism made from leucite, which is a particular crystalline form of calcium carbonate. The wave motion of emergent light is restricted to any one plane. Light whose vibration take place in only one plane is known as plane polarized light or just polarized light. The plane along which vibrations take place is known as plane of polarization, and the nickel prism used for polarizing the light is known as polarizer. Figure 2.2. Source of light, unpolarized light, then polarizer, then polarized light. Figure 2.2. Vibration in ordinary and polarized form of light. 2.5.3. Optical activity. There are certain substances which can rotate the plane of polarized light. For instance, when polarized light vibrating in a certain plane is passed through cane sugar solution, the light which emerges out vibrates in a different plane. Such substances which can rotate the plane of polarized light are said to be optically active, and the property is called optical activity. The substance which rotate the plane of polarized light towards the right are termed dextrorotatory positive, while those which rotate towards the left are called levorotatory negative. The instrument used for measuring the angle of rotation, denoted as alpha, of the plane of polarized light is known as polarimeter. The angle of rotation through which plane of polarized light is rotated by an optically active substance depends upon many factors, which are: first, nature of the compound; second, length of the liquid column through which the light passes; third, concentration of the solution and nature of the solvent in case of solid substance only; fourth, temperature; fifth, wavelength of light used. 2.5.4. Specific rotation. In order to compare the rotatory power of different substances, optical active is expressed as specific rotation. It is the angle of rotation of the plane of polarized light produced by a tube 1 decimeter 10 centimeter in length, filled with a solution having 1 gram of the substance per ml of the solution at a temperature T, using light of wavelength 5893 Armstrong from sodium vapor lamp. This light is called a D line of sodium. Specific rotation is generally calculated from the equation alpha Td, observed angle of rotation, divided by L into D. While D represents the weight in gram of solute in 1 ml of solution or density of the substance if it is a liquid, and L is the length in decimeter of the tube filled with the sample. For instance, the specific rotation of cane sugar solution at 293 Kelvin is plus 66.5 degree 293 D. 2.5.5. Elements of symmetry. The phenomena of optical activity is essentially related to lack of symmetry in molecular structure. A simple method to decide whether a molecule is symmetrical or not involves three criteria of symmetry known as elements of symmetry. An element of symmetry may be defined as a plane line or point with respect to which the structure possesses a definite symmetry. There are three elements of symmetry as discussed below. First, plane of symmetry. It is an imaginary plane passing through an object or a structure which divides the object or structure into two halves, such that one half is the mirror image of the other. For example, a beaker has a plane of symmetry as shown below in figure 2.3a. Similarly, the molecule of propanoic acid has a plane of symmetry as shown in figure 2.3b. Figure 2.3, plane of symmetry in a beaker. Figure 2.3b, plane of symmetry in propanoic acid. In the study of optical isomerism, the plane of symmetry may be shown simple with the help of a three-dimensional formula, or more conventionally by using planar formula as shown in figure 2.4a and 2.4b for the molecule of 2,2-dibromobutane. Figure 2.4a, three-dimensional representation. Figure 2.4, planar representation. Human hand is the most perfect example of an object having no plane of symmetry. 2-chlorobutane, lactic acid and alanine are some examples of molecules which do not have any plane of symmetry. 2-chlorobutane, lactic acid, alanine. CH3, CHCl, CH2, CH3, COOH, CHOH, CH3 lactic acid, COOH, CHNH2, CH3 alanine. Second, center of symmetry. It is an imaginary point within a molecule at which all the straight lines joining identical points in the molecules cross each other. For example, the center of symmetry in a molecule of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid is shown below in figure 2.5. Figure 2.5, center of symmetry in 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid. It may be noted that a structure can have more than one plane of symmetry, but no structure can have more than one center of symmetry. 3. Axis of symmetry. It is an imaginary line passing through the molecule so that when the molecule is rotated about this line, exactly similar geometrical arrangement appears more than one in one complete revolution, that is, in a rotation through 360 degrees. If the identical arrangement appears twice in one complete revolution, that is, after every 180 degrees, the axis is called two-fold axis of symmetry, denoted as C2 axis. If the similar arrangement appears thrice, it is threefold axis of symmetry, and so on. For example, trans 1,2-dibromo cyclopropane possesses a C2 axis of symmetry in the plane of the ring, which dissects the bond between carbon atom 1 and 2 and intersects the carbon atom 3 as shown in figure 2.6. When rotated about this axis, the same arrangement appears after every 180 degree. Figure 2.6, C2 axis of symmetry. Alternating axis of symmetry or rotation reflection axis. This is another element of symmetry which is rarely used. A molecule is said to have an n-fold alternating axis of symmetry if rotation by an angle of 360 divided by n about the axis followed by reflection in a plane perpendicular to that axis gives a molecule which cannot be distinguished from the original molecule. For example, 1,3-diethyl 2,4-dimethyl cyclobutane possesses a two-fold axis of symmetry as shown below. If the molecule A is rotated by an angle of 180 degree, that is 360 degree by 2, about the axis S2 which passes through the center of the ring, it gives a molecule B. The reflection of B in a plane perpendicular to the axis gives the original molecule A. Rotation of 180 degree 360 degree divided by 2 about S2 gives B, then reflection in plane perpendicular to S2 gives C. It may be noted that a one-fold alternating axis of symmetry corresponds to a plane of symmetry, while a two-fold alternating axis of symmetry corresponds to center of symmetry. Problem 2.1. Which of the following molecules have a plane of symmetry? First, propanoic acid. Second, 2-methyl-butanol. Third, 2-methyl-cyclohexone. Fourth, aminoethanoic acid. 2.5.6. Molecular chirality, chiral and achiral structures. First, chiral structures. A structure or object is said to be chiral or dissymmetry if it is non-superimposable on its mirror image. Such a structure does not have either a plane or a center of symmetry. The most perfect example of a chiral object is human hand. It does not have any plane of symmetry and cannot be superimposed on its mirror image. If you hold your left hand up to a mirror, the image looks like a right hand, but if you try to superimpose one hand over the other, both palm downs, you cannot do it. Figure 2.7. Similarly, a right-handed glove and a left-handed glove are chiral objects. Figure 2.7. Non-superimposable mirror images. A very large number of organic molecules such as 2-chlorobutane and lactic acid are known to have chiral structures as they are not superimposable on their mirror images. 2-chlorobutane, lactic acid, non-superimposable mirror images. The substance having chiral structures are said to possess the property of chirality. It should be noted that chirality is the property of complete object or structure and not of its parts. It may also be noted that even though there are three kinds of elements of symmetry, chirality is primarily related to lack of plane of symmetry and the center of symmetry. Second, achiral structures. A structure or object which has a plane of symmetry and is superimposable only on its mirror image is known as achiral or symmetrical. Such structures always possess a plane of symmetry or a center of symmetry. For example, the letter A and the button on your shirt represents a chiral structure or objects. It can be easily seen that each of these has a plane of symmetry and is superimposable on its mirror image. Figure 2.8. Object A, image A, mirror. Superimposable mirror images. Dotted line represent plane of symmetry. Figure 2.8. Achiral structure. Methane and carbon tetrachloride are perfect examples of molecules having achiral structures as they are superimposable on their respective mirror images. Methane, 2-chloropropane, superimposable mirror images. Two objects are said to be superimposable if, when placed one upon the other, their corresponding parts lie together. Two objects that are like mirror images of each other may be either superimposable or not superimposable. For example, two notebooks of the same size having mirror images relationship are superimposable. But term chiral, based upon the Greek word "chaia", which means hand, was first introduced by Cahen, Ingold, and Prelog in 1964. Thus, chirality means handness, that is, the relationship which exists between the left and right hand. In recent years, the terms chiral and chirality has almost completely replaced the old terms disymmetry and dissymmetry, respectively. Third, origin of chirality in organic compounds. Most of the organic compounds which are chiral in nature owe their chirality to the presence of a carbon atom bonded to four different groups. Such a carbon is termed as a chiral carbon or chiral center or a stereogenic center or stereocenter, earlier known as asymmetry carbon. Stereogenic center or chiral carbon is a carbon atom which is bonded to four different monovalent atoms or groups such as C, A, B, C, D. There can be two different tetrahedral models for C, A, B, C, D, which differ in the spectral arrangement of various groups attached to the carbon, as shown in Figure 2.9. Figure 2.9, non-superimposable mirror images models of CABCD. Each of the two models is related to the other like an object to its mirror image, and one cannot be superimposed on the other, no matter how we turn or twist them. Each of these models therefore represents a chiral structure. Similarly, when we can have two non-superimposable mirror image structures for any compound which contains a stereogenic center or chiral center. For example, lactic acid CH3 star CHOH COOH and 2-methyl 1-butanol C2H5 star CH3 CH2OH are chiral molecules, since each of them contains a chiral center, the one marked star. Figure 2.10. Figure 2.10, non-superimposable mirror images model of lactic acid and 2-methyl 1-butanol. It must be emphasized, however, that certain molecules may contain more than one stereogenic or chiral center, and still they have a bichiral or achiral or non-disymmetry. For instance, 2,3-dichlorobutane CH3 CH star Cl CH star Cl CH3, which has two chiral centers, those marked star, exist in many isomeric forms, one of which is not chiral because it has a plane of symmetry as shown below. Plane of symmetry. Chiral molecules not containing any chiral carbon. There are certain molecules known to exist which are chiral even though they do not contain any chiral carbon. For example, allenes. RCH double bond C double bond CHR represents a well-known class of each compounds as illustrated below. Non-superimposable mirror images of 2,3-pentadiene. It may be seen by molecular models that chirality in 2,3-pentadiene arises due to the fact that the two groups singly bonded to one of the end carbon atoms of allene systems are in a different plane than the two groups singly bonded to the other end carbon of the allene system. Substituted biphenyls constitute another examples of such compounds which are chiral without containing any chiral carbon atom. The chirality in such compounds arises due to the fact that the two benzene rings lie in different planes perpendicular to each other. For example, non-superimposable mirror images of 6,6-dinitrophenolic acid. 2.6, Optical isomerism and enantiomerism. It has been observed that optically active substances always exist in two or more isomeric forms which differ with respect to their optical activity or their action on plain polarized light, as already stated. The isomers which resemble one another in their chemical reactions and most of the physical properties but differ in their effect on polarized light are called optical isomers, and the phenomena is known as optical isomerism. There are two main types of optical isomerisms. These are enantiomerism, second stereomerism. We shall now discuss these two types starting with enantiomerism. 2.6.1 Enantiomerism. It is the simplest kind of optical isomerism which was discovered by Pasteur in 1848 as a result of his work on the salt of tartaric acid. He observed that optically inactive sodium ammonium tartrate constituted of a mixture of two distinct types of crystal. These two types of crystals were not superimposable on each other, although their shapes were like mirror images of each other. The relationship between the two types of crystal may be compared to that between a pair of right and left-handed gloves. Picture separated the two types of crystal from the original sample with the help of a magnifying lens and a pair of tweezers. Unlike the original optical inactive samples, each type of crystal was found to be optically active in its aqueous solution. Moreover, the specific rotation of the solution of one type of crystal was found to be equal but of opposite sign to that of the solution of second type of crystals. Considering the fact that difference in optical rotation was observed in solution where the solute exists in the form of simple molecules, Pasteur proposed that the molecule constituting the two types of crystal were also non-superimposable mirror images of each other. Such isomers whose molecular structures are non-superimposable mirror images of each other and which rotate the plane polarized light equally but in opposite directions are now known as enantiomers or enantiomorphs. The phenomena of mirror images isomerism is known as enantiomerism. Since the mirror images isomers differ only in the spectral arrangement of atoms, enantiomerism represents a type of stereoisomerism. Explanation of enantiomerism. The existence of mirror image isomers or enantiomers was justified by von 't Hooft on the basis of tetrahedral concept of carbon atom. Let us try to apply this concept to an imaginary compound of the type CABCD in which a carbon atom is attached to four different groups. Such a compound can be represented by two different tetrahedral models which differ in the spatial arrangement of various groups attached to the carbon atom. Figure 3.9 on last page. The two models are related to each other like an object and its mirror images, and one cannot be superimposed over the other no matter how we turn or twist them. This model represents two enantiomers of the compound. For example, let us draw tetrahedral formula of an enantiomeric form of substance such as lactic acid CH3CH OH, COOH and 2-methyl 1-butanol C2H5CH, CH3CH2OH, which are known to exhibit enantiomerism. In each of these cases, we found that it is possible to construct two formula which are non-superimposable mirror images of each other, and as such they represent the different enantiomers. Figure 2.10 on page 210. It may be pointed out, however, that if the compound containing a tetrahedral carbon atom does not have four different groups attached to this carbon, then the molecules are superimposable on their mirror images. This is illustrated below with the help of bromochloromethane CH2ClBr. Such compounds do not exhibit enantiomerism because all these molecules are of the same type. Figure 2.11. No enantiomerism possible as mirror images of bromochloromethane are superimposable. 2.6.2 Fundamental conditions for enantiomerism. It may be shown above that enantiomeric molecules are always non-superimposable mirror images of each other. The non-superimpossibility of mirror images invariably arises due to the chiral nature of the molecule. As already stated, a molecule is termed as chiral if it has no plane of center of symmetry and is therefore non-superimposable on its mirror image. Chirality in most of the enantiomeric molecules is itself due to the presence of at least one chiral carbon in the molecule. For example, lactic acid CH3 star CH, OH, COH, and 2-methyl 1-butanol C2H5 star CH, CH3, CH2OH contains one chiral carbon each, the one marked star, and therefore exists an enantiomeric form as shown in figure 3.10 on page 310. All the same time, there can be molecules such as 2,3 pentadiene and substituted biphenyls such as 6,6-dinitrophenic acid, which do not contain any chiral carbon, but they still possess the property of chirality and thus exhibit enantiomerism. It may be concluded, therefore, that chirality, that is the property of existing as non-superimposable mirror images, is the fundamental and only conditions of enantiomerism. 2.6.3 Characteristics of enantiomerism. The important characteristics of enantiomerism of a given substance are described below. First, they have identical physical properties such as melting point, boiling point, densities, solubilities, refractive index. The only difference lies in the direction of rotation of plane polarized light, although even here the magnitude of specific rotation is the same. For example, the specific rotation of the two enantiomeric 2-methyl 1-butanol are plus 5.76 degree and 5.76 degree minus respectively. Second, they have identical chemical properties except in reactions with other optical active compounds. For example, the ordinary chemical reaction of plus lactic acid are actually like those of minus lactic acid. Moreover, there is no difference in the speed of such reactions. There may be difference, however, in the rate of reactions at which twin enantiomers react with some other optically active compounds. For instance, the rate of esterification of plus lactic acid with plus butyl alcohol CH3, CH2, CHOH, CH3, which is the optically active, would be different from the rate of esterification of minus lactic acid with the same alcohol. Third, they have different biological properties. In contrast to physical and usual chemical properties, enantiomers are quite different in their biological properties. For example, plus sugar plays an important role in animal metabolism, whereas minus sugar is not metabolized at all. Similarly, plus tartaric acid is readily consumed by the mold Penicillium glucose, while minus tartaric acid is not. Fourth, when equal quantities of enantiomers are mixed together, it results in the formation of an optically inactive form called racemic modification or racemic mixture or racemate. The racemic modification distinguished by using the prefix plus minus before the name of the compound. For example, if equal quantities of plus lactic acid and minus lactic acid are mixed with each other, we get racemic or plus minus lactic acid, which is optically inactive. 2.6.4 Enantiomerism and optical activity. We have just learned that the fundamental conditions for the phenomena of enantiomerism is the chiral nature of the molecules and the fundamental differences between enantiomers of a given substance is the direction of optical rotation. Let us now examine as to what structural features gives rise to optical activity and how is it related to the phenomena of enantiomerism. A single individual molecules of nearly every substance can cause some rotation of the plane polarized light. When a beam of such light passes through the molecule, the direction and extent of rotation caused by a particular molecule depends upon its orientation in the beam of light. But in actual practice, it is not possible to have with us only a single molecule of any substance, even a very small sample of a substance being made up of a very large number of molecules distributed at random. Therefore, what happens in most of the cases is that for every molecule that rotates the plane of polarized light, there is another identical molecule oriented as the mirror image of the first, which exactly cancels that effect. As such, no optical rotation can be observed. This means optical inactivity of a substance is basically due to the random distribution of identical molecules which can serve as mirror images of each other. But in case of chiral molecules, the mirror image of any one molecule is not another identical molecule, rather, it is a different isomeric molecule. Now, if we take a pure sample consisting of a single enantiomer, no molecule can serve as the mirror image of another. As a result, there cannot be exact cancellation of rotation, and as such, optical activity is observed. Thus, a given sample of a substance can exhibit optical activity only if the constituent molecules are non-superimposable mirror images of one another. In other words, chirality, that is non-superimposibility of mirror images, is as the fundamental and sufficient conditions for optical activity. Problem 2.2 Classify the following objects as chiral or achiral. First, shoe. Second, spoon. Third, cup. Fourth, ear. Fifth, pea. Answer chiral first, fourth, fifth. Achiral second and third. Problem 2.3 Which of the following molecules are chiral in nature? First, CH3, CH, CHCl, CH3 on second position, CH3. Second, CH2, OH, CHO, H, CHO. Third, CH3, CHO, H, CH3. Fourth, CH3, CH, CH, CH3, CH3. Fifth, phenyl CHCl CH3. Sixth, CH2 NH2 COOH. Answer 1, 2nd and 5th. Problem 2.4 Given below are the structural formula of all alkenes having the molecular formula C6H14. Which of these exhibits enantiomerism? First, CH3 CH2 4 CH3. Second, CH3 CH2 twice CH CH3 CH3. Third, CH3 CH CH3 CH CH3 CH3. 4 CH3 thrice C CH2 CH3. Fifth CH3 CH2 CH CH2 CH3. Answer: none of these can exhibit enantiomerism. Problem 2.5. Point out the optically active compounds out of the following. First, CH3CH CH2OH. Second, CH3CH2CH double bond C double bond CH single bond CH2CH3. Third, COOH CHOH CHOH. Fourth, CH2OH CHOH CHO. Answer: all are optically active. 2.7 Representation of stereoisomers. 2.7.1 Flying wedge formula. We have so far used the molecular models and a three-dimensional tetrahedral formula to represent the stereoisomers. The tetrahedral formula can also be drawn in a somewhat different but more convenient way known as flying wedge formula. For drawing this formula, the molecules is orientated in space in such a way that two bond to the stereo center point towards the observer while the other two bonds are directly away from the observer. The bonds pointed towards the observer are represented by wedges drawn horizontal, which may or may not be drawn along a straight line. The bonds pointed away from the observer are represented by hashed or dotted lines drawn vertically. For example, the molecular model, tetrahedral formula, and flying wedge formula of one of the enantiomers of lactic acid CH3CHOHCOH may be shown as follows. Molecular model: tetrahedral form COH single line, CH3 single line, and OH with the wedge line, and H with the dotted line. Flying wedge formula. Similarly, the three kinds of representations of the other enantiomers of lactic acid can be drawn as the tetrahedral and flying wedge formula of the enantiomers of 2-butanol are drawn below. 2.7.2 Planar representation of three-dimensional formula. Fisher projection formula. The use of molecular model is no doubted the most suitable method of showing the spatial orientations of atoms consisting of molecules, but is not very convenient to represent the formula of compounds on paper. Therefore, a single, although non-foolproof method was introduced by Emil Fischer 1891 for projecting three-dimensional formula of chiral molecules on planar surface. The planar representation are called Fischer projection formula. Procedure for writing Fischer projections. For writing the projection formula, the following procedures is adopted. First, the chiral molecule is viewed in such a way that the two groups bound to chiral carbon points towards the observer while the other two groups point away from the observer. Second, the various groups attached to the chiral carbon are then projected to the plane of the paper in a form of a cross so that horizontal lines represents bonds pointing towards the observer while vertical lines represents bonds pointing away from the observer. If the chiral molecules contains two or more chiral carbons, each carbon is considered separately as described above. Third, the vertical parts of the projection formula should represent so far as possible the longest chain of carbon atoms in the molecules, with the carbon atom to be numbered as 1 according to the IUPAC system being written at the top. Fourth, the chiral carbon atom is not written at all. While writing the projection formula, it is taken for granted that the chiral carbon is located where the horizontal and vertical lines cross each other. For instance, the projection formula of the two enantiomers of lactic acid may be represented as shown ahead. Molecular models and Fisher projection formula of two enantiomers of lactic acid. It should be noted that more than one Fisher projection can be written for the same compound depending upon which bonds are shown horizontally and which bonds are drawn vertically. It is therefore necessary to test whether the given Fisher projection represents the same stereoisomer of a compound or not. This can be done by using the following rules. First, a Fisher projection may be imagined to be rotated from end to end without lifting it from the plane of the paper. Rotation by 180 degree in the plane of the plane does not bring about any change in configuration. For example, if the projection first of lactic acid is rotated through 180 degree in the plane of the paper, it gives projection 2. Since no change in configuration take place in rotation by 180 degree, projections 1 and 2 represent the same stereoisomer of lactic acid. No change in configuration 1 and 2 represent the same compound. But rotation by 90 or the 270 degree leads to inversion of a configuration, that is, change one configuration into its mirror image, so that the new configuration represents the enantiomers of the original compound. Third, minus lactic acid, rotation through 90 degree. Fifth, plus lactic acid, inversion of configuration. Third and fourth represent the two enantiomers of lactic acid. Second, if position of two groups or atoms about the chiral carbon are interchanged, it also leads to inversion of configuration. But if we carry out two such interchanges, the configurations remain unaltered. Fifth, minus lactic acid. First, interchange position of H and OH interchanged. Sixth, plus lactic acid, inversion of configuration. Second, interchange position of H and CH3 interchange. Seventh, minus lactic acid, configuration same as that of fifth. It is quite evident from above that one interchange is equivalent to rotation by 90 degree or 270, while two interchanges are equivalent to rotation by 180 degree. 2.8 Chiral and achiral molecules with two stereogenic centers, distereomerism. We have learned that a compound containing one stereogenic center exists in two stereoisomeric forms, which are known as enantiomer of each other. What about compounds containing two stereogenic centers? Quite acceptedly, such compounds can exist in more than two stereoisomeric forms. To illustrate this statement, let us consider the case of 2,3-dichloropentane CH3CH2CHClCHClCH3, which contains two stereogenic centers. Since the four different groups attached to one stereogenic center are not the same as thus attached to the other, the two chiral carbon atoms are dissimilar from the another. There are as many as four stereoisomers, one, second, third, fourth, possible for this compound. One pair of enantiomers, second pair of enantiomers. Examination of a formula first and second reveals that they are no superimposable mirror images of each other and hence represent a pair of enantiomers. Similarly, third and fourth are also non-superimposable mirror images of each other and as such represents another pair of enantiomers. Let us now compare the formula first with the formula third. Same configuration, mirror images configuration first and third. It becomes immediately clear that the two formula have identical configurations about one chiral carbon C2, but mirror image configuration about the other chiral carbon C3. The net result is that the two forms are neither identical nor mirror images of each other. Such stereoisomers of a substance which are not mirror images of each other are known as distereomers. In addition to formula first and third, formula first and fourth, second, third, second and fourth also represent a pair of distereomers. Fisher projection formula and flying wedge representations of the four stereoisomers of 2,3 dichloropentane are given below. Fisher projection formula. Flying wedge form representations. Dichloro-2-butanol affords another example of a compound having two similar chiral carbon atoms which can exist in four stereoisomeric form as given below. Fifth, fourth, seventh, eighth. It may be seen that structure fifth and seventh, fifth and eighth, sixth and seventh, sixth and eighth represents pair of distereomers. Characteristics of distereomers. The important characteristics of distereomers are as follows. First, they show similar but identical chemical properties. In the reactions of two distereomers with a given reagent, the rates of reaction are generally different from each other. This is because distereomers have different energies of activation for a particular reaction and therefore they react at different rates. Second, they have different physical properties such as melting point, boiling point, density, solubility, and refractive indexes. Third, their specific rotation are also different for each other. In fact, some of the distereomers may be even optically inactive. It should be noted that geometrical isomers are also distereomers of each other, but they are optically inactive. Fourth, on account of different physical properties, distereomers can be rather easily separated from each other by physical methods such as fractional crystallization, fractional distillation, chromatography, etc. Comparison of distereomers and enantiomers. Distereomers. First, they are stereoisomers which do not have a mirror image relationship. Enantiomers. They are stereoisomers which have a mirror image relationship. Second, these have different physical properties such as melting point, boiling point, solubility in a given solvent, and density. They have identical physical properties such as melting point, boiling point, solubility in a given solvent, and density. Third, they can be separated by fractional distillation, fractional crystallization, and adsorption chromatography. Enantiomers. This cannot be separated by such methods. Distereomers. This may have optically rotation in the same or opposite directions but to a different extent. Enantiomers. These have optical rotation in opposite directions but to the same extent. Distereomers. Fifth, they have identical chemical properties but different in the rates of reaction with optically active compounds. Enantiomers. They have identical chemical properties except with other optically active compounds. 2.8.1 Erythro and stereoisomers. A special system of nomenclature is sometimes used for distinguishing between distereomers in which two of the atoms or group attached to one stereogenic center are the same as the two atoms or groups attached to the other stereogenic center. This method is derived from the name of two distereomeric carbohydrates, erythros, in which similar groups are on the same side, and steros, in which similar groups are on the opposite sides, as shown below. Erythros, steros. If the two similar groups are on the same side in the Fisher projection formula of a molecule, the distereomers is known as
erythroisomers. If the two similar groups are on the opposite sides in the projection formula of a molecule, the diastereomers is known as stereoisomers. For example, of the four isomers of 3-chloro-2-butanol, one pair of enantiomers is known as erythro, while the other pair of enantiomers, which are diastereomers of the first pair, is known as stereo, are illustrated below. Erythro 3-chloro-2-butanol, one pair of enantiomers. Thero 3-chloro-2-butanol, other pair of enantiomers. It may be seen that any one compound of one pair is diastereomers of any one compound of the other pair. The names erythro and thero are derived from the names of two simple sugars, erythros and theros, which having the following configurations. 2.9 Mesocompounds. Let us now consider a compound containing two similar chiral centers, that is, having the same set of four different groups attached to each of the chiral carbon atom. A typical example of such a compound is provided by tartaric acid, CHOH, COOH, twice, then CHOH, COOH. In view of the fact that it has two chiral centers, one may accept the existence of four stereoisomers of this acid having the configuration 9th, 10th, 11th and 12th. Pair of enantiomers. Superimposable mirror images represent only one compound. Formula 9th and 10th are non-superimposable mirror images of each other and therefore represent a pair of optically active enantiomers. Formula 11th and 12th again have a mirror image relationship. Close examination of this formula, however, shows that one of these structures may be superimposed on the other just by rotating it through 180 degrees within the plane of the paper. These two formula therefore represents two superimposable mirror images molecules of the same compound. Further examination of formula 11th or 12th reveals that in spite of two chiral centers in it, the molecule is achiral. This is because it has a plane of symmetry, one half of its molecules being a mirror image of the other half. As such, the compound represented by formula 11th or 12th is optically inactive. Such an optically inactive compound whose molecules are not chiral even though they contain two or more chiral centers is known as a mesocompound. As explained above, the molecule of such compounds are superimposable on their mirror images, plane of symmetry. The tartaric acid exists in three forms: minus tartaric acid, plus tartaric acid formula 9th and 10th, and mesotartaric acid formula 11th or 12th. Although optically inactive, the mesotartaric acid represents a diastereomer of minus or plus tartaric acid. Fischer projection formula and flying wedge formula of three stereoisomers of tartaric acid are given below. Fischer projection formula, flying wedge formula, representation. It should be noted that mesocompounds are permanently inactive and are said to be internally compensated. This is because one half of the molecule cancels the rotation due to the other half. 2,3-dichlorobutane affords another example of a compound which contains two chiral carbon and exists in the three forms, two optically active forms and one mesoform. 2.10 Number of possible stereoisomers in compounds containing different number of chiral centers. It may be stated that the maximum possible number of stereoisomers of a molecule is 2 n when n is the number of chiral centers in the molecule. Thus, the molecules having 1, 2 and 3 chiral carbon atoms exist in 2, 4 and 8 stereoisomeric form respectively, but the actual number may be less than the maximum if some of the isomers exist in mesoform. It is possible to predict the actual number of stereoisomers by simple calculation as explained below. First, when the molecules contain n stereogenic centers, n may be odd or even number, and the molecule has no plane of symmetry. Number of optically active isomers D and L forms 2 power n. Number of mesoforms is equal to 0. Total number of isomers 2 power n plus 0 is equal to 2 power n. For example, 2,3-dichloropentane, CH3CHCl, CHCl, CH2CH3, two stereogenic centers exist in the form of 2 power 2 4 is equal to 4 optically active isomers as already shown on page 216. Second, when the molecule contains n stereogenic centers where n is equal to an even number and the molecule has a plane of symmetry, number of optically active forms is equal to 2 power n minus 1. Number of mesoforms is equal to 2 power n divided by 2 minus 1. Total number of isomers is equal to 2 power n minus 1 plus 2 power n by 2 minus 1. For example, tartaric acid HOOCCHOHCHOHCOOH. Two stereogenic centers with a plane of symmetry exist as 2 power 2 minus 1 is equal to 2 optically active isomers and 2 power 2 divided by 2 minus 1 is equal to 2 power where 0 is equal to 1 mesoform. Total number of isomers is equal to 2 plus 1 is equal to 3, already shown on figure 217. Third, when the molecule contains n stereogenic centers where n is equal to an odd number and the molecules may have a plane of symmetry, number of optically active forms is equal to 2 power n minus 1 is minus 2 power n minus 1 divided by 2. Number of mesoforms is equal to 2 n minus 1 divided by 2. Total number of isomers is equal to 2 power n minus 1 minus 2 power n minus 1 divided by 2 plus 2 power n minus 1 divided by 2 is equal to 2 power n minus 1. For example, pentane minus 2, 3, 4, triol CH3 CHOH 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 CH3. Three stereogenic centers with a possible plane of symmetry exist as 2 power 3 minus 1 minus 2 power 3 minus 1 divided by 2 is equal to 2 power 2 minus 2 is equal to 2 optically active form. 2 power 3 minus 1 divided by 2 is equal to 2 mesoforms. Total number of isomers is equal to 2 plus 2 is equal to 4. These isomers are shown below. Optically active, meso. It is possible to draw 4 more structures, but each one of these would be found to be superimposable on one or the other of the above structures, as can be shown by rotation through 180 degree within the plane of the paper. Problem 2.6. Which of the following compounds can have a mesoform? First, 2,3-dichloropentane. Second, 2,4-dichloropentane. Third, 2,4-dichlorohexane. Answer: second can have a mesoform. Problem 2.7. How many stereoisomers are possible for the following compound? CH3, CHF, CHCl, CHBr, CH3. How many of them are optically active? 8. All are optically active. Problem 2.8. Draw a structure which is a diastereomers of the structures given below but is not optically active. CH3, CH2, CHOH, CHOH, CH2, CH3. Answer: CH3, CH2, CHOH, CHOH, CH2, CH3. 2.11. Racemization. It has been stated earlier that an optically inactive mixtures containing equal quantity of enantiomers of a substance is known as racemic mixture or racemates. It is denoted by using the prefix plus minus or DL or RS before the name of the compound. For example, a racemic mixture of lactic acid is denoted as plus minus lactic acid. Racemic mixtures can be formed in one of the following three ways. First, synthesis of chiral compounds from achiral reactants. Please see Sec 3.14. Second, mixing of equal amounts of two enantiomers already described. Third, racemization. We will now consider the process of racemization and its mechanism. 2.11.1 Racemization. The conversion of an optically active compound into a racemic mixture containing equal amount of original compounds and its enantiomer is known as racemization. Racemization can be brought about by one of the following methods depending upon the nature of the compound. First, by the action of heat. Quite often an optically active enantiomer changes into a racemic mixture by the action of heat. For example, when plus tartaric acid is strongly heated with the water, it gets converted into a mixture of racemic and mesotartaric acids. Second, by the action of chemical reagents. Racemization is also brought about by the presence of a foreign substance, particularly acid and bases, in the solution of an optically active substance. For example, addition of sodium hydroxide to plus or minus lactic acid leads to the formation of a racemic mixture. Third, auto-racemization. In some cases, racemizations take place by merely keeping the substance at room temperature for some time. This is known as auto-racemization. For example, any one of the enantiomers of dimethyl bromate changes into a racemic mixture on standing at room temperature. Mechanism of racemization. Different mechanisms has been developed by the racemization of different types of compounds, but in the majority of cases, racemization is believed to take place through the formation of some intermediate which is no longer chiral in nature and explained ahead. Acid catalyzed racemization of an optically active aldehyde or ketone in which the chiral carbon carries a hydrogen and is in alpha position with respect to the carbonyl group takes place through annualization, that is, the intermediate formation of an achiral anole by tautomer exchange, with the anolic form being unstable, reverts the chiral keto form, but in doing so, it produces plus and minus enantiomers in equal quantity, and thus racemization takes place. This is shown ahead with the help of a 3-methyl-2-pentanone plus keto form, then H positive minus H positive, then enolic form, loss of chirality, then minus keto form. Irrespective of whether the starting compound is plus or minus 3-methyl-2-pentanone, the final product is a racemic mixture since both the enantiomers are formed in equal quantities. Base catalyzed racemizations of minus lactic acids take place through the formation of an achiral carbanion as shown below. Minus enantiomers gives water plus loss of chirality, then equilibrium with water gives plus enantiomers. The final product would be a racemic mixture whether we start minus or plus enantiomers of lactic acid. We will come across many examples of chemical reactions in the text, such as SN1 reactions of alkyl halides discussed in chapter 9, which are accompanied by complete or partial racemization. Partial racemizations means that one enantiomers may be formed in large amount than the other so that the mixture of the two will not be completely inactive. 2.12 Internal and external compensation. 2.12.1 Internal compensation. It has been stated above that meso compounds are optically inactive because their molecules are not chiral even though they contain two or more chiral centers. For example, it is clear from the structural formula of mesotartric acid that the top half of the structure is the mirror image of the bottom half. As such, the optically active due to one chiral center is counterbalanced by the optically active due to the other, and the compound is optically inactive. The counterbalancing of optically active of one half of a molecule by the other half is known as internal compensation, and the molecule is said to be internally compensated. An internal compensated molecule is permanently inactive. 2.12.2 External compensation. In an equimolar mixture of two enantiomers, say plus and minus lactic acids, the molecule of one enantiomers are present in a quantity equal to those of the other enantiomers. This means that for every possible orientation of one enantiomers which can cause rotation in a particular direction, say towards right, a molecule of the other enantiomers would be in a mirror image orientation which would cause a rotation in the opposite direction. Therefore, exact cancellation of all rotations would take place and the equimolar mixtures would be optically inactive. The cancellation of rotation of one enantiomers by the other in a equimolar mixture of two enantiomers is known as external compensation, and the racemic mixture is said to be externally compensated. It may be pointed out that if the two enantiomers are not mixed in equimolar quantities, the rotation caused by one enantiomer is not exactly cancelled by the other. As such, this mixture still exhibits some optically activity. The direction of rotation corresponds to that of the enantiomers present in large quantity, but the specific rotation is lesser. In this way, partial compensations take place and the mixture formed is said to be partially racemized. Comparison of external and internal compensation. External compensation. Internal compensation. External compensation. First, this is due to the mirror image relationship between the structures of the molecules of two enantiomers mixed together. Internal. It is due to the mirror image relationship between the structures of two halves of the same molecule. External. In this type of compensation, the molecules of one enantiomers cancel the rotation of the other enantiomers. Internal. In this type of compensation, one half of the molecule counterbalances the rotations of the other half. Third, the racemate formed is external. The racemate formed is a mixture of two isomeric compounds. Internal. Meso or internally compensated compounds represent a single pure compound. External. It is possible to have complete or partial external compensation of rotation so as to cause complete or partial racemization. Internal. Partial internal compensation is not possible. External. It is a reversible process and the racemic mixture can be resolved into minus and plus enantiomers. Internal. It is a permanent effect and is not possible to resolve an internally compensated molecule into optically active forms. 2.13 Resolution of racemic mixture. The process of separating a racemic mixture into its enantiomers is called resolution. It is not easy to carry out resolution in actual practice. This is because enantiomers have identical physical and chemical properties which make their separations from each other very difficult. Therefore, special methods has been introduced for this purpose. 2.13.1 Mechanical separation. If the enantiomers of a substance exist in well-defined crystalline form, the separation can be done by hand picking with the help of a magnifying lens and a pair of twingers. For example, the enantiomers of sodium ammonium tartrate can be separated by this method. Limitations. First, this method has a very limited application as very few enantiomeric substances exist in the form of mechanical separable crystals. Second, the method is very laborious and time consuming. 2.13.2 Biochemical separation. This method involves the use of microorganisms for bringing about resolution. If certain bacteria, yeast, or mold are allowed to grow in a dilute solution of a racemic modification, one of the enantiomers is selectively consumed by the microorganisms while the other is left behind. For example, when the mold Penicillium glaucum is allowed to grow in a solution of ammonium tartrate, the mold completely dissolves plus ammonium tartrate, while negative ammonium tartrate is left practically unaffected. Limitations. First, the main disadvantage of this method is that one half of the material is destroyed during separation. Second, as the separation is carried out only in dilute solutions, the process is very slow and only small amount of material can be separated. 2.13.3 Chemical separation. It is probably the best method of resolution. It involves the conversion of racemic mixtures into a mixture of distereomers of some other substance by reaction with an optically active reagent. Since diastereomers have different physical properties, the mixture of diastereomers can be easily separated through fractional crystallization, fractional distillation, chromatography, etc. Each of the diastereomers is then suitably treated to generate a pure enantiomers of the original substance. For example, if a racemic mixture of plus and minus lactic acids is treated with a single enantiomer of an optically active base, say minus brucine, it would result in the formation of a mixture of two crystalline salts. The two salts formed would be minus brucine plus lestate and minus brucine minus lestate. While brucine part of these salts have the same configuration in both cases, the acid parts has no superimposable mirror images configuration in two cases, so that the two salts represent two diastereomers. As such, the crystal of two salts differ in their solubility and can be separated by fractional crystallization. Once the separation has been achieved, the reaction of each salt with hydrochloric acid would generate a free lactic acid in pure enantiomeric form. Plus minus lactic acid plus minus brucine gives minus brucine plus lacetate plus minus brucine minus lacetate can be separated by fractional crystallization. Minus brucine plus lacetate plus HCl gives plus lactic acid get crystallized plus minus brucine HCl remain in solution. Minus brucine minus lacetate plus HCl gives minus lactic acid gets crystallized plus minus brucine HCl remains in solution. Apart from the separation of racemic acid or bases by this method, it can also be employed from the separation of racemic alcohols, aldehyde, etc. by treatment with the suitable optically active reagents. 2.13.4 Chromatography. These days, chromatographic techniques such as adsorption chromatography using optically active adsorbents, paper chromatography, and glass chromatography are also being used for resolution. In adsorption chromatography, the solution of racemic mixture in a suitable solvent is passed through a column packed with optically active adsorbent. When differential adsorption of the enantiomers takes place, this is followed by elution with suitable solvents to get each enantiomer separately. 2.14 Asymmetric or enantioselective synthesis. It has been already pointed out that when a chiral compound is synthesized from a chiral compound, the product obtained is in the form of racemic mixture. For example, propanoic acid in presence of Br2P gives racemic mixture of plus and minus alpha bromopropanoic acid. CH3CH2COH in presence of Br2P gives CH3CHBrCOH and CH3CHBrCOH. The racemic mixture has been to be resolved into the enantiomers through method described on previous pages. It is, however, found that if the chiral compound is prepared by a chiral compound under the influence of some optically active substance, which is subsequently removed, the product found is optically active. This method of directly preparing and optically active isomers from achiral molecules under the influence of some other optically active substance is called asymmetric or enantioselective synthesis. It may be pointed out that even in asymmetrical synthesis, both the plus and minus enantiomers are formed, but one of these are obtained in predominating amount so that the product exhibits a net optical rotation. The following examples illustrate the applicability of this process. First, synthesis of minus lactic acid. Lactic acid obtained by the direct reduction of puric acid as such is found to be in the form of a racemic modification. However, if puric acid is first esterified with optically active alcohol such as a minus methyl alcohol and the ester formed is subjected to reduction and then hydrolysis, we get a product having excess of minus lactic acid. CH3C double bond O COOH pyruvic acid plus C10H19OH minus methyl alcohol gives CH3C double bond O COO C10H19 minus methylene pyruvate. Then reduction gives CH3CHOH COO C10H19 minus methyl lactate, and then hydrolysis gives COOH CHOH CH3 minus lactic acid main product plus C10H19OH minus methyl alcohol. Second, synthesis of minus mandelic acid. Mandelic acid C6H5CHOH may be obtained in racemic form by the reaction of benzaldehyde with hydrogen cyanide followed by hydrolysis. But when the same synthesis is carried out in the presence of an enzyme emulsion like most other enzymes, it is also optically active. Minus mandelic acid is found to be the main product. C6H5CHO benzaldehyde in presence of HCN gives C6H5CHOHCN. Mandalonitrile mandalonitrile then hydrolysis gives C6H5CHOHCOH minus mandelic acid, main product obtained in the presence of emulsin. Most of the chiral compounds formed in nature, such as alkoxides and proteins, are obtained in optically active form. This is because they are synthesized in nature under the influence of other optically active species. Prochirality prochiral atom. It has been shown above that the replacement of one of the hydrogens attached to C2 of a propanoic acid, which is optically inactive, by bromine gives rise to a racemic mixture of optically active products. This is because C2 is originally achiral in nature, but in the product formed it becomes chiral. Such an atom is known as a prochiral. A prochiral atom may be defined as the central atom in a molecule, the replacement of one of the H atom attached to which by a substituent atom or a group generated a chiral center. The molecules containing the prochiral atom is known as prochiral molecule, and the phenomena is called prochirality. CH3CH2COH prochiral atom, propanoic acid, prochiral molecule in presence of replacement of H by Br gives CH3CHBrCOH chiral carbon and CH3CHBrCOH racemic mixture of plus and minus bromopropanoic acid. 2.15 Inversion of configuration. Weldon inversion. If an atom or group of atoms directly attached to a stereogenic center is substituted by some other atom or group, the configuration of new compound is sometimes found to be different from that of the original compound. This is known as inversion of configuration or optical inversion. This phenomena was first discovered by Weldon and is therefore also known as Weldon inversion. For example, first, when minus chlorosucenic acid is treated with aqueous potassium hydroxide, the product obtained is plus malic acid having a different configuration than the starting compound. COOH, CHCl, CH2COH minus chlorosucenic acid in presence of aqueous KOH gives COOH, CHOH, CH2COH plus malic acid. Inversion of configuration. Second, when treatment with the aqueous KOH minus 2-bromo-octane gives plus 2-octanol, which has configuration opposite to that of a minus 2-bromo-octane, that is CH3CHBrC6H13 minus 2-bromo-octane in presence of OH negative gives CH3CHOH C6H13 plus 2-octanol. Inversion of configuration. It may be noted, however, that a change in configuration may or may not be accompanied by change in direction of rotation. Retention of configuration. If a compound containing a stereogenic center is converted into another without breaking any of the bonds with the stereogenic center, the product has the same configuration as the original compound. This means that the reaction proceeds with the retention of configuration. For example, COOH CHOH CH2Br minus 3-bromo-2 hydroxypropanoic acid in presence of ZnHCl gives COOH CHOH CH3 minus lactic acid, same configuration. 2.16 Configuration and its specification. 2.16.1 Configuration. The arrangement in space of the atom or group constituting a stereoisomer is called its configuration. For example, the configurations of the two enantiomers of lactic acid are first and second shown below. One of them, this configuration represents dextro or plus lactic acid, while the other represents levio or minus lactic acid. 2.16.2 Specification of configuration D and L notation. When we state that one of the enantiomer of lactic acid has the configuration first while the other has the configuration second, given above were merely represented the two possible configuration of the enantiomers of lactic acid. What is not indicated in which configuration represents which isomer, that is the enantiomers of lactic acid. What is not indicated in which configuration represents which isomers, that is which one of the two isomers plus and minus has the configuration first and which has the configuration second. In other words, we do know the exact actual or absolute configuration of each of the two enantiomers. In the earlier days of the study of stereochemistry, it was not found possible to determine the absolute configuration of the compound. Fortunately, it is not always necessary to know the absolute configuration of an optically active compound. On the other hand, we are more interested in knowing the relative configurations of different compounds. For example, when an optically active compounds undergo chemical reactions, we are mainly interested in whether the configuration of the reactant and its product are same or different and not in their actual configuration. Relative configurations. Standard reference compound. To assign relative configurations to various optically active compounds and to indicate their relationship, what was done was to choose a standard reference compound and fix its configuration arbitrarily as proposed by M.L. Fisher 1885. The compound chosen as the standard was glyceraldehyde CH2OH CHOH CHO, and its two enantiomers were designated by the symbol D, read as D, and L, read as L. It must be made clear that the symbol D and L refer to the configuration are quite different from the prefix D and L, read as dextro and levio, which represents to the direction of rotation. Plus, glyceraldehyde was arbitrarily assigned the configuration 3, in which the OH group attached to chiral carbon is towards right and was given the symbol D. The minus enantiomers was assigned the configuration 4, in which the OH group attached to chiral carbon is towards left and was given by the symbol L. D plus glyceraldehyde, L minus glyceraldehyde. Three-dimensional and planar representation of two enantiomers of glyceraldehyde. Reason for selecting a glyceraldehyde as the standard. Glyceraldehyde was chosen as the standard mainly because of the following reasons. First, it is the simple carbohydrate and aldotreose, and its configuration could be easily related to the other carbohydrates, which are stereochemically very important compounds. Second, since glyceraldehyde contain very reactive functional groups, it could be converted into many other types of compounds. In this way, it could be configurationally related to a large number of compounds. Correlation of configuration. Many other compounds were then assigned relative configurations by relating their configurations to that of D or L glyceraldehyde. For this purpose, either the compound under examination is converted into D or L glyceraldehyde, or D or L glyceraldehyde is converted into the given compound by means of reactions which do not involve glyceraldehyde is converted into the given compound by means of reactions which do not involve breaking of bonds to a chiral center. The general principle involved in correlating the configuration of two compounds is that if a reaction does not involve the breaking of a bond about a chiral center, the configurations about the stereogenic center remains unchanged. Some important examples of the correlations of the configurations are given below. First, minus glyceric acid can be obtained by the oxidation of D plus glyceraldehyde as shown below. Since these reactions do not involve breaking of bonds about the stereogenic center, minus glyceric acid must have the same configuration as that of glyceraldehyde taken, that is D configuration. CHO, CHOH, CH2OH, D plus glyceraldehyde in presence of O, Br2 and presence of H2O gives COOH, CHOH, CH2OH, D minus glyceric acid. Second, the configuration of plus lactic acid was established to a similar to that of L minus glyceraldehyde by the following reactions. CHO, CHOH, CH2OH, L minus glyceraldehyde in presence of O, Br2, H2O gives COOH, CHOH, CH2OH, L plus glyceric acid. Then in presence of PBr2 gives COOH, CHOH, CH2Br, L plus 3 bromo 2 hydroxypropanoic. Then reductions give COOH, CHOH, CH3, L plus lactic acid. None of the reaction involves breaking of bond about the stereogenic center. Third, when D positive glyceraldehyde was converted into tartaric acid by the series of reactions shown below, a mixture of two products was obtained. These two products differed from each other in their configuration around a newly created stereogenic center marked star. One of the product was inactive or mesotartaric acid. Fifth, the other was the optically active tartaric acid, which rotated the plane of light to the left, that is, it was a minus tartaric acid. Since it was obtained from glyceraldehyde by reactions which did not involve breaking of bonds around the original chiral center, it was assigned D configurations that is the same as that of the starting glyceraldehyde. CHO, CHOH, CH2OH, D plus glyceraldehyde in presence of HCN2 configuration possible around new stereogenic center marked star. CnCHOH, CHOH, CH2OH, then hydrolysis BaOH twice, then gives COOH, CH star, OH, CHOH, CH2OH in presence of O or HNO3 gives COOH, CH star, OH, CHOH, COOH. Fifth, mesotartaric acid. CN, CH star, OH, CHOH, CH2OH. Hydrolysis BaOH twice gives COH, CH star, OH, CHOH, CH2OH. In presence of O, HNO3 gives COH, OH, CH star, CHOH, COH. Sixth, D minus tartaric acid. Since D minus tartaric acid was assigned configuration, sixth L plus tartaric acid would naturally have the mirror image configuration, that is Seventh, COH, CHOH, CHOH, COH. Sixth, D minus tartaric acid, COH, CHOH, CHOH, COH. Seventh, L plus tartaric acid. It must be emphasized that there is no direct relationship between absolute configuration and the direction of rotation of polarized light. Two substances may have similar reactive configuration and light may rotate the plane of light in different directions. For example, D plus glyceraldehyde plus D minus glyceric acid have similar configuration even though the former is dextrorotatory while the latter is levorotatory. CHO, CHOH, CH2OH, D plus glyceraldehyde, COH, CHOH, CH2OH, D minus glyceric acid. Similarly, two compounds may have a different configuration and even then they may rotate the plane of polarized in the same direction. For example, D plus glyceraldehyde plus L plus lactic acid have opposite configuration but the same sign of rotation. CHO, CHOH, CH2OH, D plus glyceraldehyde, COH, CHOH, CH2OH, L plus lactic acid. 2.16.3 Absolute configuration. It was only in 1951 that by using X-ray diffraction studies, Weizmann was able to determine the absolute configuration of a compound, that is, the actual arrangement in space of that or groups constituting a particular stereoisomer. The main compound was absolute configuration was determined was sodium rubidium salt of plus tartaric acid. Weizmann found that plus tartaric acid actually have the same configuration which it was previously assumed to have on the basis of configurational relationship between glyceraldehyde and tartaric acid as described above. If the assumed configuration relationship between glyceraldehyde and tartaric acid as described below, if the assumed configuration of plus tartaric acid was correct, the assumed configuration of the two enantiomers of glyceraldehyde must also be correct. As such, the configuration of all other compounds derived by correlation with the glyceraldehyde must be correct ones. Thus, the relative configuration assigned to D minus glyceric acid, L minus lactic acid discussed above, carbohydrates, and a large number of other compounds actually represents their absolute configurations. The absolute configurations of some simple but stereochemically important compounds are given below in the planar form. CHO, CHOH, CH2OH, D plus glyceraldehyde, CHO, CHOH, CH2OH, L minus glyceraldehyde, COH, CHOH, CH3, D minus lactic acid, COH, CHOH, CH3, L plus lactic acid, COH, CHOH, COH, CHOH, CHOH, CH2OH, D minus tartaric acid, COH, CHOH, CHOH, COH, L plus tartaric acid. 2.16.4 Limitations of D plus L system of configurations. The system of designating the configuration as D and L is essentially based upon the configurational relationship to one or the other enantiomer of glyceraldehyde, but the procedure followed has certain limitations. It has been found that in some cases a given compound can be related by a sequence of reactions to a known compound having D configuration, but at the same time by another sequence of reactions the given compound can also be related to the L enantiomer of the known compound. This leads to an ambiguous situation where the same compound may be assigned either D or L configuration. It may, however, be pointed out that in the case of carbohydrates and amino acids, certain conventions has been adopted due to which the system of assigning D and L configuration is found very useful in these classes of compounds. 2.17 Rectus and semester or R and S sequence for specification of configuration. In view of the limitations of D and L system of configurations, Cahen, Ingold, and Prelog suggested a very simple procedure to specify a particular configuration of a substance in terms of prefixes R or S. The procedure involves the following two steps. Step 1. The four atoms or groups of atom bonded to the chiral center are assigned a sequence of priorities in accordance with a set of rules known as sequence rules. The sequence rules are as follows. Rule 1. If all the four atoms directly attached to the chiral center are different from one another, sequence of priorities is determined by their atomic numbers. The atom of highest atomic number gets the highest priority, while the one with the lowest atomic number comes last in order of priority. For example, in the compound 1-bromo 1-chloroethane CH3 star CHCl the four groups attached to chiral carbon are CH3, HCl, and Br. Their sequence of priorities will be Br, then Cl, then CH3, then H. Similarly, the order of priorities of the group CH3, OH, NH2, and H is OH, then NH2, then CH3, then H. If two isotopes of the same element are involved, the isotopes with the higher mass number gets higher priority. For example, out of hydrogen H11 and deuterium H10, deuterium gets a higher priority. Rule 2. If the first atom of two or more groups attached to the chiral center have the same atomic number, the relative priorities may be fixed by comparing the next atom in the group. If even this does not solve the problem, the comparison may be extended further to the next atom and so on. For as an example, in sec-butyl alcohol, the relative priorities of CH3 and C2H5 are decided as follows. Each of these groups is linked to a chiral center through the same atom, that is carbon. The next atom in CH3 are HHH, while in C2H5 they are CH and H. Since carbon has a higher atomic number than hydrogen, C2H5 gets higher priority than CH3. CH3, CH2, CHOH, CH3. Therefore, the complete sequence of priorities is OH, then CH3, CH2, then CH3, then H. Rule 3. If a group contains a double or triple bond between two atoms, it is treated as equivalent to two single bonds or three single bonds between the two atoms. In other words, each pi bond is supposed to be broken and atoms at each end of the pi bond are duplicated. While doing so, two imaginary atoms are added for each pi bond broken. For instance, C double bond X is treated as equivalent to CXC. X and C are imaginary atoms added due to breaking of a pi bond. Thus, it is considered that the group C double X contains two atoms of X attached to carbon. Similarly, C triple Y is treated as equivalent CYYYCC. Therefore, the group C triple bond Y is considered to contain three atoms of Y attached to carbon. To take a specific example, in the group CH double bond O, next atom to carbon are equivalent to OO and H, that is CHO is treated as equivalent to CHO and OC, that is there are two atoms of O and one atom of H attached to carbon. Therefore, if we compare the group CHO and CH2OH, the former gets higher priority as in its the atoms next to carbon are OO and HO, while CH2OH they are OH and H. Comparison of the priorities of some typical groups. Let us compare the relative priorities of vinyl CH double bond CH2 and isopropyl CH3 CH CH3 groups In isopropyl group, the first carbon is attached to two carbons and a hydrogen. In vinyl group also, the first carbon is treated as linked to two carbons and a hydrogen. CH3 CH CH3 CH the double bond CH2 triple bond CHC CHHC. But in vinyl group, the second carbon is further attached to one carbon C and two hydrogens. On the other hand, in isopropyl, the second carbon is attached to only hydrogens. Therefore, vinyl group get priority over isopropyl group. Similarly, phenyl group gets priority over acetylenic group C triple bond CH. Phenyl group is considered as if it has one of equal structures, that is treated as equivalent to C C H C H C C C C C H C H. Acetylenic group C triple bond CH is equivalent to C, then 2C, C, H, then 2C. In both, the first carbon is taken as attached to three carbons. In phenyl, two of the three carbons attached to first carbon are further attached to two carbons and a hydrogen, while the third is a duplicate carbon. In acetylenic group, only one of the three carbons attached to the first carbon is further attached to two carbons and a hydrogen, while the other two are duplicated carbons. Therefore, phenyl group gets priority over acetylenic group. It is very evident that phenyl or acetylenic group would get priority over vinyl or isopropyl groups. This is because in phenyl or acetylenic group, the first carbon is attached to three carbons, while in vinyl and isopropyl, the first carbon is attached to only two carbons. Thus, the order of priorities of this group would be C6H5, C triple, then C triple bond CH, then CH double bond CH2, then CH3 CH CH3. Relative priorities of some common groups. To sum up the above discussion on the determination of priorities of different groups, we give below the relative priorities of some common groups in increasing order of priorities. H CH3 CH3 CH2 CH3 CH CH3 CH2 double bond CH CH3 thrice C N triple bond C H O CH2 H C double bond O CH3 C double bond O H C double bond O NH2 OH CH3O F HO3S Cl negative Bri. Step 2. Having decided the sequence of priorities, the molecule is imagined to be in position where the group of lowest priority is directed away from us. And now we look at the arrangement of remaining groups is decreasing order of their priority, that is the highest or number first downwards. If in doing so the eyes travel in clockwise direction, the configuration is specified as R Latin rectus is equal to right. If on the other hand, if the eye travels in anti-clockwise direction, the configuration is specified as S Latin sinister is equal to left. Let us illustrate the above rules by considering some specific examples. First, chloroidomethane sulfonic acid CHCl SO3H. The sequence of decreasing priorities of group attached to stereogenic carbon is first I, second Cl, third SO3H, and 4H. To assign configuration to it, the isomer shown below is held in a position so that H, which has the lowest priority, is pointed away from the observer. Now, if the remaining groups are arrived in order of decreasing priorities, that is I, then Cl, SO3H. The I has to travel in clockwise manner as shown ahead, therefore the configuration of the isomer is R. Proceeding in the same manner, the configuration of the enantiomeric form of the above structure would be S. Second, lactic acid CH3CHOH. The sequence of priorities in decreasing order is OH, COH, CH3H. Therefore, the specific configuration of the two enantiomers of the lactic acid may be designed as third 2-chlorobutane CH3CHCl2H5. The sequence of priorities is Cl C2H5 CH3H. Therefore, a specific configuration of its enantiomers may be given as 2.17.1 configuration on the basis of a projection formula. While assigning configuration to a stereoisomer on the basis of a projection formula, two kinds of situation may arise. First, if the groups of lowest priority is bonded vertically, that is pointing away from the observer, the configuration is assigned by following exactly the same procedure as in case of a three-dimensional formula. For example, in the structure given below, the sequence of priorities is Cl, then phenyl CH, double bond CH2, then H. The group of lowest priority, that is H, is bonded vertically, that is pointing away from us. The moment of the ice is moving from Cl to phenyl to CH, double bond CH2 in anti-clockwise. Therefore, configuration is S. Second, if the groups of lowest priority is bonded horizontally, that is pointing towards the observer, an additional step is required. In such, the given formula is converted into another equivalent projection formula by making two interchanges so that the atom or group of lowest priority is placed vertically downwards or upwards. Then the configuration is assigned by following the usual procedure. For example, second, assigning of configuration to the given isomer of 2-butanol CH3HCH2 CH3OH. First interchange H and OH. Second interchange H and CH2 CH3. The sequence of priorities is OH, CH2, CH3, CH3H. After the second interchange, H is bonded vertically in the projection formula in moving from OH to CH. To CH3 to CH3, the ice travels in anti-clockwise direction, therefore configuration is S. Third, assignment of a configuration to a given isomer of 2-aminopropanol. First, interchange H and NH3, then second interchange NH2 and CH3. The sequence of priorities is NH2 CHO CH3H, therefore configuration is R. It may be recalled that if we carry out two interchanges of the groups attached to the carbon, the configuration remains equivalent to the original configuration. 2.17.2 Configuration of compounds containing more than one chiral center. In such case, the configuration about each chiral center is ascertained separately. The specification of each atom along with its number is then prefixed before the name of the compounds as illustrated below. First, let us consider one of the forms of tartaric acid given on the right hand side. Each chiral center, carbon 2 and carbon 3, in this molecule has the same sets of four groups attached to it, that is COH, HOH and CHOH, COH. The sequence of priorities of this group is OH, COH, CHOH, COH, H. The configuration around C2 may be assigned as follows. Since the I has to travel clockwise in moving from OH to COH to CHOH, COH, the configuration around C2 is R. Similarly, the configuration around C3 may be assigned as follows. It may be seen that configurations around C3 is also A. Thus, the configurations around each of the chiral center is S, so that the compound may be designed R2, R3, R tartaric acid. Second, let us now assign configuration to the compound. Each of carbon atoms 2 and 3 has the group CH3, HCl and CHCl, CH3 attached to it. The order of purities of group is Cl, CHCl, CH3, CH3H. Configuration at C2 can be known as follows. Configuration at C3 can be obtained as follows. Hence, the configuration of the above compound is 2s3r. Useful shortcut for assigning configuration to Fisher projection formula. Decide the sequence of priorities of the four atoms or groups attached to the chiral carbon. Determine the configurations without making an interchange in the given projection formula. If the atom or group of lowest priority is bonded vertical either upward or downward in the projection formula, the configurations determined as above gives the actual configuration. If the atom or group of lowest priorities is bonded horizontally either left or right in the projection formula, change the configuration obtained above from R to S or vice versa to get the actual configuration. For example, without making any interchanges, the configuration obtained is S. Since the atom of lowest priority, that is H, is bonded vertically, this represents the actual configuration. Without making any interchanges, the configuration obtained is R. Since the atom of lowest priority, that is H, is bonded horizontally in the projection formula, change R to S. Therefore, without making any interchanges, the configuration obtained is S. Since the atom of lowest priority, that is H, is bonded horizontally in the projection formula, change S to R. Therefore, actual configuration is R. Problem 2.9. Arrange the following groups in decreasing order of priorities. A. C triple bond N. B. CHO. C. CH2 NH2. D. CH double bond CH2. E. Phenyl. F. CH2 CH3. G. C double bond O NH2. Answer G, then B, then A, then C, then E, then D, then F. Problem 2.10. Assign R and S configuration to the following. First, Cl CH2 C Cl CH3 CH CH3 twice. Second, COH CHOH CHOH COH. Third, CH NH2 COO C2H5 COH. Fourth, phenyl CHNH2 CH CH3 twice. Fifth, CH2 double bond CH CHBr CH2 CH3. Sixth, CH3 CHOH CHCl CH3. Hint: no interchanges are required for first, fourth and fifth. Answer: first S, second 2s, 3s, third R, fourth R, fifth R, sixth 2R, 3s. 2.18. Geometrical isomerism, hindered rotation around carbon-carbon double bond. 2.18.1. Geometrical isomerism and its causes. Geometrical isomerism is a type of stereoisomerism which is exhibited by certain compounds containing double bonds and arises due to hindered rotations about the double bond. We will first discuss geometrical isomerism in compounds containing carbon-carbon double bond and then considered other types of compounds which also exhibit geometrical isomerism. A carbon-carbon double bond contains of a sigma and a pi bond, while the sigma bond is formed by overlapping of sp2 hybridized orbital of two carbon atoms along the internuclear axis. Pi bond is below the plane of atoms. Because of this type of overlapping rotation around carbon-carbon double bond is strongly hindered and can take place only if the pi bond breaks, but this would require about 284 kilojoule of energy per mole, which is not available to the molecules at room temperature. Due to hindered rotations around carbon-carbon double bond, the relative positions of groups attached to doubly bonded carbon atoms get fixed. As a result, several higher alkenes and other substituted products can exist in two distinct isomeric forms which differ from each other in the relative distribution of groups in space around the double bond. For example, malic acid and formic acid afford a very well known example of compounds which exist in geometrical isomeric form as shown below. CHCOH double bond CHCOH malic acid, CHCOH double bond CHCOH fumaric acid. These two isomers are like one another with respect to which atoms are attached to which other atoms but differ from each other in the relative arrangement of atoms in space. In malic acid, the two carboxylic groups lies on the same side of the molecules, while in formic acid, the two carboxylic groups lies on opposite sides. Such isomers which have the same structural formula but differ in the relative spatial arrangement of atoms about the double bond are called geometrical isomers, and the phenomena is known as geometrical isomerism. It is obvious that geometrical isomerism represents a type of stereoisomerism, since the stereoisomerisms which are not mirror images of each other are distereomers. Geometrical isomers can also be regarded as distereomers. It may also be pointed out that in case of optical and geometrical isomers, the different structures of optical or geometrical isomers cannot be interconverted except by breaking or making of bonds. As such, these two types of stereoisomers are also collectively known as configurational isomers. 2.18.2 Conditions for geometrical isomerism. These are two necessary conditions for a compound to exhibit geometrical isomerism. These are: first, the molecules must contain a carbon-carbon double bond, the rotation around which is strongly hindered. Second, each of two doubly bound atoms should bound atoms should have two unlike groups attached to it, as for instance ABC is equal to CAB. The formula ABC is equal to CAB can have two arrangements in space which represent the geometrical isomers as shown below. A C B double bond CAB. Similar groups on same side of double bonds. A, B, C, double bond C, B, A, similar groups on opposite sides of double bond. For example, 2-butene CH3 CH double bond CH CH3 exist in the form of geometrical isomers as depicted below. CH3 CH double bond CH CH3 CH3 CH double bond CH CH3 geometrical isomers of 2-butene. Sometimes the two groups attached to one doubly bonded carbon may be altogether different than those attached to the other carbon atoms, such as ABC is equal to CCD. Even the geometrical isomers would be exhibit, however, this is not essential condition. ABC double bond CDE, ABC double bond CED. Compounds like propene and 2-methylpropene contains carbon-carbon double bond but still do not display geometrical isomerism. This is because one or other carbon involved in the formation of a double bond carry two similar groups as shown below. CH2 double bond is CH3 propene, CH2C double bond CH3 CH2 methyl propene. No geometrical isomers possible. 2.18.3 Nomenclature of geometrical isomers cis and trans system. The method originally used for denoting the configuration of geometrical isomers is known as cis-trans system. In this system, the names of the geometrical isomers have different configurations are distinguished by using the prefix cis, which means on the same side, or trans, which means across, before the name of the compound. The prefix cis is used when similar groups are on the same side of the molecules, which the prefix trans is used when similar groups are on opposite sides, as illustrated below. CH3CH double bond CH CH3 cis to butene, CH3CH double bond CH CH3 trans to butene, HCl double bond C HCl cis 1 to dichloroethene, CHCl double bond CHCl trans 1 to dichloroethene, Br CH double bond CHBr cis 1 to dibromoethene, CHBr double bond CHBr trans 1 to dibromoethene, CHCOH double bond CHCOH malic acid cis, CHCOH double bond CHCOH fumic acid trans. Limitations of cis and trans system of nomenclature. The cis and trans system of nomenclature of geometrical isomers is not universally applicable. It cannot be employed in case of compounds where all the four substituents attached to the doubly bonded carbon atoms are different from each other. That is, ABC is equal to CED. For example, let us consider the following compound CFCl double bond CBRI. Here we can see that I and Cl are cis to each other, but we can also equally well say that Br and Cl are trans to each other. Therefore, it becomes difficult to name such a substance either as cis or trans isomer. 4. E and Z system of nomenclature. In view of the limitations of the cis-trans system, a more general system of nomenclature of geometrical isomers known as E and Z system is now being adopted. EZ system is based upon the sequence rules originally developed by Cohen, Prelog, and Ingold for R and S systems of specifying configurations of optical isomers. Please refer to SEC on R and S system for specifying the configuration of geometrical isomer as E or Z. The following rules are followed. First, the two atoms or groups attached to each carbon of the double bond are assigned a higher or lower priority according to the priority sequence rule of R and S system of optical isomers. Second, if the higher priority atom or group on each carbon of the double bond are on the same side, the configuration is designed as Z from the German Jusman is equal to together. On the other hand, if the atom or group of higher priority are on opposite sides, the configuration is termed as E. For the German antigon is equal to across, then we have Z is equal to 1 bromo, 2 chloro, 2 fluoro, 1 iodoethene. E 1 bromo, 2 chloro, 2 fluoro, 1 iodoethene. We know that atoms having higher atomic number has higher priority. Therefore, out of F and Cl attached to C1, Cl has a higher priority. In the same way, out of Br and I attached to C2, I has the higher priority. Some more examples of assigning E and Z designation are given below. CH3, CH double bond, CH3, CH high, CH3 higher, H lower, CH3 higher, H lower, Z to butene, CH3 higher, CH lower, double bond, CH lower, CH3 higher, E to butene. COH higher, C CH3 lower, double bond C, Cl higher, H lower, Z3 chloro 2 methyl 2 propanoic acid, CO OH higher, C, CH3 lower, double bond CH lower, Cl higher, E3 chloro 2 methyl 2 propanoic acid, CH lower, COH higher, double bond CH lower, COH higher, malic acid Z, CH lower, COH higher, double bond CH lower, COH higher, fumaric acid E. It may be noted that most of the compounds that we would normally design cis are designated Z. Similarly, most of the compounds that we designate trans are designated E. 2.18.5 Nomenclature of compounds containing more than one double bond. If a compound containing two or more double bonds are around which geometrical isomerism is possible, E and Z designations are given to each double bond. For example, CH3, CH double bond CH, CH double bond CH, CH3, 2Z, 4Z, 2, 4 hexadiene, CH3CH double bond CH, CH double bond CH, CH3, 2E4Z, 4 hexadiene, CH3CH double bond CH, CH double bond CH, CH3, 2Z4E2 4 hexadiene, CH3CH double bond CH, CH double bond CH, CH3, 2E4E2 4 hexadiene. Problem 2.11. Of the following structures, which will exhibit geometrical isomerism? First, CH3CH double bond CCl2. Second, CH3CH2C, CH3 double bond CH, CH2 CH3. Third, CH2 double bond CH double bond CHCl. Fourth, CH3 CH2 CH double bond CH, CH2 CH3. For the compounds which exhibit geometrical isomerism, draw the structures of their isomers and name them as cis or trans. Answer: second and third exhibit geometrical isomerism. Second, CH3 CH2 C CH3 double bond CH CH2 CH3 cis 3 methyl hex 3 CH3 CH2 C CH3 double bond CH CH2 CH3 trans 3 methyl hex 3 Third, CH2 double bond CH CH double bond CHCl cis 4 chloro buta 1 3 diene CH3 CH2 double bond CH CH double bond CHC trans 4 chloro buta 1 3 diene. Problem 2.12. Assign EZ configuration to the following compounds. First, CH3CH double bond CHCOH. Second, ICBr double bond C6H5NHCH3. Third, CH3CH double bond CDCH3 twice. Fourth, CH3CH double bond CDH. Fifth, CH3CH double bond CHCHO. Sixth, COH CH3 double bond CCl COCH3. Answer: first E, second E, third E, fourth Z, fifth E, sixth Z. 2.18.6 Determination of configuration of geometrical isomers. The following methods can be employed for determining the configurations of geometrical isomers. First, from dipole moment. Determination of the dipole moment of a pair of geometrical isomers can be quite helpful in designating a particular isomer as cis or trans. For instance, in case of compounds of the type ABC is equal to CAB, the net dipole moment of a trans isomer is accepted to be zero. This is because the similar groups are on opposite sides of the molecule and therefore the bond polarities cancel out each other. In contrast, the bond polarities are not cancelled in case of cis isomer and therefore it has a definite dipole moment. The cis-2-butene should have a small dipole moment while the dipole moment of trans-2-butene should be zero. The following experimental data goes to support the above prediction. CHCl double bond CHCl cis 1,2 dichloroethene dipole moment is equal to 1.85 d. CHCl double bond CHCl trans 1,2 dichloroethene dipole moment is 0. BRCH double bond CHBr cis 1,2 dibromoethene dipole moment 1.35 d. BRCH double bond Br trans 1,2 dibromoethene dipole moment is 0. Second, from boiling point. In general, cis isomers have higher boiling point than trans isomers. This is evidently because of the higher polarities and higher dipole moment of cis isomers, which leads to greater intermolecular attractions. For example, the boiling point of cis-2-butene is 277 Kelvin, while that of trans isomers is 274 Kelvin. CH3CH double bond CH3 cis-2-butene boiling point 277 Kelvin. CH3CH double bond CH3 trans 2-butene boiling point 274 Kelvin. Third, from melting points. Generally speaking, trans isomers have higher melting points than cis compounds. This is because trans isomers are more symmetrically and can be more closely packed in the crystal lattice. For example, CHCOH double bond CHCOH malic acid cis melting point 403 Kelvin. CHCOH double bond CH3COH fumic acid trans 575 Kelvin. Fourth, from the formation of ring compounds, sometimes it is possible to distinguish between two geometrical isomers by chemical reactions. Chemical reactions which leads to the formation of rings. Cis isomer is likely to undergo ring closure much more readily than the trans isomers. For example, malic acid cis form loses water when heated to 423 Kelvin to form a malic anhydride ring compound. On the other hand, fumaric acid transform does not give the anhydride at this temperature. CHCOH double bond CHCOH malic acid cis form in 423 Kelvin and minus H2O gives COCH double bond malic anhydride ring compound. CHCOH double bond CHCOH 423 Kelvin, no reaction. 5. By conversion into compounds of known configurations. Sometimes a particular geometrical isomers can be converted into a compound of known configuration without any change in configuration around double bond. From the configuration of the product formed, the configuration of the starting compound can be deducted. For example, one of the geometrical isomers of trichlorochronitic acid CCl3CH double bond CHCOH on hydrolysis yield fumaric acid, while the other isomers do not. Since fumaric acid has a trans configuration, the isomers of trichlorochronitic acid, which changes into fumaric acid, must also be the trans form, that is CHCCl3 double bond CHCOH trans trichlorochronitic acid gives CHCOH double bond CHCOH fumaric acid trans. CHCCl3 double bond CHCOH does not form fumaric acid. Sixth, from the formation of type of optical isomer. In certain reactions, geometrical isomers having carbon-carbon double bond change into products having newly created stereogenic centers from the type of optical isomer formed. The cis or trans nature of the starting compound can be determined. For example, malic acid on hydroxylation with KMnO4 gives mesotartric acid, while fumaric acid forms a racemic mixture of tartric acid as shown below. CHCOH double bond CHCOH malic acid cis form in presence of KMnO4 gives OHCHCOH CHCOH OH or COH CHCOH CHCOH OH mesotartric acid. CHCOH double bond CHCOH fumaric acid transform gives OHCHCOH CHCOH OH plus OHCHCOH CHCOH OH racemic or plus minus tartric acid. 2.18.7 Geometrical isomerism in compounds other than alkenes. Geometrical isomerisms can also be exhibited by compounds in the molecules of which there may be hindered rotations due to some other reasons that the presence of carbon-carbon double bond. Thus, geometrical isomerism is also shown by compounds having carbon-nitrogen double bond oximines, nitrogen-nitrogen double bonds, azo compounds, and even some cyclic compounds which do not contain any double bond as discussed below. First, geometrical isomerism in oximines. Oximines are the compounds formed by reactions between aldehyde or ketones and hydroxyamine, that is CO aldehyde or ketone plus NH2OH gives C double bond NOH. For example, CH3CH double bond O plus NH2OH gives CH3CH double bond NOH plus water. Acetaldehyde converted into acetic oxamine. C6H5C CH3 double bond O plus NH2OH gives C6H5Cl CH3 double bond NOH plus water. Oximes exhibit geometrical isomerisms due to hindered rotations around a carbon-nitrogen double bond, while the doubly bound nitrogen carries only OH group attached to it. The doubly bound carbon must have two unlike groups attached to it for geometrical isomerisms to be possible. For example, CH3CH double bond NOH geometrical isomerisms of acid aldoxamine CH3CH double bond NOH. The configurations of geometrical isomers of oxamine are usually denoted by prefixes sin and anti instead of cis and trans respectively. In case of aldoxamine exomines, the isomers is named as sin if OH group attached to nitrogen is on the same side as attached to carbon. If the OH attached to a nitrogen is on the opposite side to hydrogen, the isomer is called anti. In case of ketoxames, the isomer is named as sin if the OH group attached to nitrogen is on the same side as the group attached to carbon, which comes first in the name of a compound. If they are on opposite sides, the name is anti. For example, CH3CH double bond NOH psi and CH3CH double bond NOH anti. SLT oximines C2H5 CH3 double bond NOH sin C2H5 CCH3 double bond NOH anti. Ethyl methyl ketoxamine Determination of configuration of oxymenes. The actual configuration of geometrical isomers of aldoxymenes is determined by their relative ease of dehydrations. When treated with a dehydrating agent such as acetic anhydride, an anti-aldoxymines undergoes dehydration easily to form nitriles. For example, RCH double bond NOH anti-aldoxymine in presence of AC twice AC2O minus H2O gives R C triple bond and nitrile. On the other hand, when a cyanitrile is treated with acetic anhydride followed by aqueous solution of sodium carbonate, original oxamine is regenerated. The configuration of ketoxamines are determined on the basis of a Beckmann rearrangement. When treated with an acidic reagent such as PCl5, P2O5, and SOCl2, the oxamine undergoes a rearrangement to form a substituted amide. The structure of the amide thus formed helps to establish the configuration of the oxamine. However, the detailed procedure would be discussed later. Second, geometrical isomerism in alkyl alicyclic compounds. There are many substituted alicyclic compounds which show geometrical isomerism. This is because the presence of a ring can also prevent a rotation around carbon-carbon single bond. Therefore, geometrical isomers become possible if there are two carbons on a ring, each of which is attached to two unlike groups. These two carbons may or may not be adjacent to each other. For example, dimethyl cyclopropane exists in two geometric form, one in which the two methyl groups are on the same side of the ring and the other in which they are on the opposite sides of the ring as shown below. Cis dimethyl cyclopropane, trans dimethyl cyclopropane. Similarly, cyclobutane 1,3-dicarboxylic acid and cyclopentane 1,2-diol also exhibit geometrical isomerism. Cis-cyclobutene 1,2-dicarboxylic acid, trans-cyclobutane 1,2-dicarboxylic acid, cis-cyclopentane 1,2-diol, trans-cyclopentane 1,2-diol. It may be pointed out that E and Z nomenclature is not used for cyclic compounds. 2.19 Conformations. It is well known that a single or sigma bond between two atoms is formed by overlapping of their orbitals along the internuclear axis. The electron distribution of the sigma bond thus formed is therefore symmetrical around the axis as shown in figure 2.12. For a single bond between sp3 hybridized orbitals of two carbon atoms, due to its sexual symmetry, the single bond allows freedom of rotation about it. As a result of this, the molecules of a compound can have different relative arrangements of their atoms in space, which can be converted one into the other by rotations around the single bond. Such arrangements in space of the atom in a molecule that can be readily interconverted by rotations around single bond are called conformations or conformational isomers. The existence of different conformations of a compound constitute a special type of stereoisomerism. We will discuss some aspects of this phenomena with reference to alkenes and cycloalkenes. Figure 2.12 Symmetrical electron distribution representing a single bond between sp3 hybridized orbitals of two carbon atoms. 2.19.1 Conformation of ethane. Ethane is the simplest molecule for which an infinite number of conformations are possible. The central bond in the molecule of ethane is a single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of the carbon atom of ethane is allowed to rotate around the central bond, while the other is held still. A very large number of arrangements of the hydrogens of one carbon with respect to the hydrogens of the other carbon can be obtained. The basic structure of the molecule and various bond lengths and bond angles, however, remain the same in all these arrangements of conformations. Of the infinite number of possible conformations of ethane, two conformations represent the extremes. These are called the ellipsed conformation and the staggered conformation. In the ellipsed conformation, the hydrogen of one carbon are directly behind those of the other. In the staggered conformation, the hydrogen of the two carbon atoms are staggered with respect to one another. Figure 2.13 and 2.14. 2.19.2 Representation of conformations. Since it is not very convenient to represent three-dimensional formula on paper, certain conventions has been adopted for projecting the conformations on paper. The two commonly used methods are as follows. First, Sawhorse formula or Andrian formula. In this representation, the molecule is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and of a relative greater length for the sake of clarity. The lower left hand carbon is taken as front carbon and the upper right hand carbon as the back carbon. The three atoms or group attached to each carbon are shown tetrahedrally in space. The sawhorse representation of ellipsed and staggered configurations of ethane are shown in figure 2.13. CH3 CH3 ellipsed, CH3 CH3 staggered. Figure 2.13 Sawhorse representation of ellipsed and staggered conformations of ethane. Second, Niemann projection formula. Niemann devised a very simple method of projecting three-dimensional formula on paper, which are known as Niemann projections. In these formulas, the molecules is viewed from the front. The carbon atom nearer to the eye is represented by a point or dot, and the three atoms or groups are shown attached to it by three lines at an angle of 120 degrees to each other. The carbon atom farther from the eye represented by a circle, and a three atom or group are shown attached to it by shorter lines ended at the circumferences of the circle at the angle of 120 degrees to each other. Niemann projections for ellipsed and staggered conformations of ethene are shown below in figure 2.14. Ellipsed, staggered. Figure 2.14 Niemann projection for the conformations of ethene. 2.20 Difference between conformations and configuration. Conformations as stated below. Conformations are three-dimensional arrangements in space of the atoms in a molecule that can be interconverted merely by rotation around single bond. For example, figure 3.13 depicts two such arrangements known as ellipsed and staggered conformations of ethene, which are readily interconvertible by rotation around carbon-carbon single bond. Configurations. As already studied, configurations are three-dimensional arrangements in space of the atoms in a molecules that cannot be interconverted merely by rotation about a bond. For example, the configurations of minus lactic acid and plus lactic acid, which are not interconvertible by rotation about the bond, as shown below in figure 2.15. COH, CHOH, CH3 minus lactic acid, COH, CH3OH plus lactic acid. Figure 2.15 Conformation of minus and plus lactic acid. In the light of above definition, the main point of difference between conformation and configurations may be summed up as follows. Conformations. These are three-dimensional arrangements in space of the atoms in a molecule which are interconvertible by rotation around a single bond. Configurations. These are three-dimensional arrangements in space of the atoms in a molecules which are not interconvertible by rotation around a bond. Uh, Conformations. Their interconversion does not require any breaking and making of bonds. Configurations. Their interconversion is possible only through breaking and making of bonds. Conformations. Their existence leads to the phenomena of conformational isomers. Configurations. Their existence is involved in the phenomena of geometrical and optical isomerism, which are also collectively known as configurational isomerism. Conformations. Since conformations are readily interconvertible, they cannot be isolated from each other. As such, configuration isomers exist only a mixture of different configurations. Since configurations are not easily interconvertible, they can be isolated from each other and stored as pure substance. As such, configurational isomers can exist as pure individual substance. 2.21 Conformational analysis of ethane. It has been stated earlier that a single bond allows freedom of rotation around it. However, it must be pointed out that rotation around the single bond is not completely free. If it is were so, the potential energy for different conformations of a compound should have been the same. But in actual practice, the potential energy of the molecule changes somewhat with the rotation around the CC single bond. The study of energy changes which occur in a molecule due to rotation around CC single bonds is known as conformational analysis. Let us first study the energy changes that taken place in ethane. The potential energy of an ethane molecule is a minimum for the staggered conformation, increases with rotation and become maximum for the elliptic conformation. The difference between the two extreme conformations being 12.55 kilojoule per mole, figure 2.16. This difference in energy constitute an energy barrier to rotation around the single bond. The energy barrier to rotation in ethane is said to be due to torsional strain, and the energy required to rotate the ethane molecule about the carbon-carbon bond is called torsional energy. This term are explained a little later in Sec 2.24. Figure 2.16 changes its potential energy during rotation about CC single bond of ethane. The energy barrier to rotation described above is, however, no larger enough to prevent rotation altogether. Even at ordinary temperature, the molecule possesses sufficient thermal or kinetic energy to overcome the energy barrier through effective collisions, and thus the conformations keep on changing from one to the other. In other words, rotation around the single bond can still take place nearly freely, being only slightly restricted by the energy barrier. As such, it is not possible to separate different conformations or staggered conformation due to its minimum energy and therefore maximum stability. In other words, any molecule spends most of its time in the staggered conformations, which is the most stable conformation. 2.22 Conformational analysis of propane. If one of the hydrogen of ethane is replaced by another atom of or group, the situation remains practically unchanged. For example, let us consider the case of propane, in which one of the hydrogen atom of ethane has been replaced by a methyl group, that is CH3CHCH3. In propane, rotation can take place about either of the two carbon-carbon bonds, even though the methyl group is considerably larger than hydrogen. The energy difference between the two extreme conformations, ellipsed and staggered, is 13.8 kilojoule per mole, which is nearly the same as in case of ethane. The most stable and preferred conformation is, of course, the staggered conformations, although it can almost freely change into the ellipsed conformation and vice versa. Ellipse staggered. Figure 2.17 Niemann projection for the conformation of propane. 2.23 Conformation analysis of N-butane. The molecule of N-butane, which may be considered as the di-substituted ethane, is somewhat more complex for conformation studies. If we consider the rotation only around the single bond between the two inner carbon atoms C2 and C3 of N-butane, we have a molecule similar to ethane but with a bulky group, that is a methyl group in place of an hydrogen atom of each carbon, CH3, CH3. In contrast with ethene and butane can have several different staggered and ellipsed conformations due to the presence of the methyl group. Four of the important conformations are anti-ellipsed, Gaussian and fully ellipsed. They are shown in figure 2.18. Anti-ellipsed, Gaussian, fully ellipsed, Gaussian ellipsed. Figure 2.18. Important conformations of n-butane. The anti-conformation first is an extreme staggered conformations in which the methyl group are as far apart as possible. If the angle of rotation around the C2C3 single bond is assumed to be 0 for this conformation, and one of the C2 or a C3 carbon atom is rotated through an angle of 60 degree, an ellipsed conformation second results. In this conformation, the methyl group attached to one carbon is not at all back of the methyl group attached to the other carbon, but is at the back of hydrogen attached to the carbon. Rotation by another 60 degree leads to another staggered conformation called Gauche conformations. Third, in which the two methyl groups are only 60 degree apart. Further rotation by 60 degree gives rise to a fully ellipsed conformation. Fourth, in which two methyl groups are at the back of each other. On further successive rotation by 60 degree, we pass through another Gauche conformation, fifth, and another ellipsed conformation, sixth, and finally arises at the anti-conformation again on completion of 360 degree. The difference in energy content between conformation 1 and 4th is about 18.4 kJ per mole. Between 1 and second or 6th, about 14.6 kJ per mole, and between 1 and 3rd or 5th, only about 3.8 kJ per mole, as shown in figure 2.19. Figure 2.19. Change in potential energy during rotation about C2C3 single bond of N-butane. Therefore, the order of stability of different conformations of N-butane is anti, then Gauche, then ellipsed, then fully ellipsed. It is apparent that due to very small difference in their energies, anti-conformation is only slightly more stable than Gauche conformation. The difference in the energy of anti and Gauche forms is due to steric strain, which is discussed in Sec 3.24. It can be easily seen that the rotation about the carbon-carbon single bond in N-butane is again nearly free, and the different conformations can not be isolated. At any time, N-butane consists mainly of an equilibrium mixture of anti and Gauche conformation, with the anti conformation having the highest percentage, about 67%, at 295 Kelvin. It will be interesting to compare the special arrangements of the two Gauche conformations, third and fifth, of N-butane. It may be easily seen that these two conformers are also mirror images and hence enantiomers of each other. Such conformational isomers, which are also mirror images of each other, are known as conformational enantiomers. However, unlike conformational enantiomers, conformational isomers are readily interconvertible by rotation about a bond. If we compare the anti-conformation first of N-butane with its Gauche conformers third and fifth, it is found that first and second or first and fourth are not mirror images of each other. Such pair of conformers are termed as conformational distereomers. Thus, we find that conformational isomers can also exist as pair of enantiomers or distereomers, which, however, are readily interconvertible. 2.24 Factors which influence conformational stability. Having discussed that rotation around single bond is not entirely free and that different conformations of a molecule have slightly different energy or stabilities, we would now consider the factors which influence conformational stability. First, torsional strain. This is the basic factor which influences the stability of a conformation. It is believed to be due to the interaction between the electron cloud of the bonds attached to the central bond around which rotation is being studied. For instance, in the molecule of ethane, there are six carbon hydrogen bonds attached to the central carbon carbon bond. In the staggered conformations of ethane molecule, the electron cloud of these carbon hydrogen bonds are as far apart as possible. But when the staggered conformation changes to ellipsed formation informations, this electron cloud rotate closest to each other. Naturally, there must be some repulsive interaction between the electron clouds affecting the stability of a conformation is known as torsional strain. As a result of torsional strain, the energy of the ellipsed conformation is more than that of staggered conformation, and consequently its stability is less. The energy required for the rotation around a single bond on account of torsional strain is called torsional energy. It constitutes the basic energy barrier to rotation about a single bond. In case of ethane, the entire difference in energy between the staggered and ellipsed conformations, that is 12.55 kilojoule per mole, is due to torsional energy or torsional strain. It is because no other factor affecting the energy or stability of conformation has any applicable influence. In this case, the situation is practically the same in propane. Second, steric strain due to van der Waals forces. When the hydrogen atoms attached to the two singly bonded central carbon atom are replaced by a bulky atom or group, another factor called steric strain being to influence the energy or stability of different conformations. Steric strain arises out of a van der Waals forces or repulsion between the different parts of the same molecule. To understand their influence, let us go back to the molecule of n-butane. Here, two hydrogens, one each of the two central carbon atom, have been replaced by two bigger methyl groups. These methyl groups are farthest apart in case of anti-conformations of n-butane, but are brought closer to in gauge and ellipse conformation figure 3.19 due to the crowding together of bulky groups. In these conformations, van der Waals forces of repulsion come into play between these groups and cause a steric strain in the molecule. Due to this strain, the energy of the molecule increases and its stability decreases. For instance, if we compare the anti and gauge conformations of n-butane, both are free of torsional strains due to their staggered nature, but gauge conformation is subjected to steric strain due to the nearness of this staggered nature. But gauge conformation is subjected to strain due to nearness of a methyl group which are only 60 degree apart, which while the anti-conformation is free from the strain also. That is why the energy of gauge conformation is slightly 3.2 kilojoule per mole more than that of anti-conformation, and its stability is correspondingly less. If we consider the fully elapsed conformation of n-butane, it is immediately obvious that both torsional and static strain are operating to the maximum in this case. Accordingly, its energy is higher than that of anti-conformation, which is free of torsional strain as well as static strain, by as much as 18.4 kilojoule per mole, and its stability is the least of all the conformation. It may be pointed out that the steric strain does not have any applicable influence in case of propane, as only one carbon atom carries a methyl group. Ordinarily, van der Waals forces are considered to operate between the non-bonded atoms of different molecules and are attractive in nature. But these forces can also operate between the different parts of the same molecule, and here the forces can be either attractive or repulsive depending upon the nature and size of groups and their relative locations. Third, dipole-dipole interaction. In case of molecules having partial polar bond attached to the central single bond, dipole-dipole interaction can occur between the different parts of the same molecule in the conformations in which oppositely charged poles are close together. The dipole-dipole interactions are attractive in nature and therefore have a stabilizing effect. On the other hand, in the conformation in which similar charged poles are brought together. These interactions are repulsive and therefore have a destabilizing effect. For example, if we consider the different conformations, figure 2.20 of 1,2-dibromoethane CH2Br, it is evident that the most stable and preferred conformations would be the anti-conformation. This is because this conformation has practically no van der Waals repulsion between the bulky bromoatom, as well as practical no dipole-dipole repulsion between the negative ends, that is bromine end of the polar bonds. Figure 2.20. Important conformations of dibromoethane. Fourth angle strain. For sp3 hybridized carbon atom, the normal bond angle is 109 degree 28 minute. Any deviations from this angle leads to an angle strain, which makes the conformation less stable. This factor operates in case of cycloalkenes and other cyclic compounds. This is discussed in the chapter or of cycloalkenes. 2.25 Conformation of cyclohexene. We have so far studied the conformation of open chain compounds. Let us now have a look at the conformation of cycloalkenes by considering the case of cyclohexene. Cyclohexane is a multiplanar or puckered ring compound in which carbon atoms are in sp3 hybridized state and all the bonded angles are equal to normal tetrahedral angle. Of the various possible conformations of cyclohexane, the two most important conformations are first chair conformation and second boat conformation. First chair conformation. This is the most stable and therefore the most preferred conformation of cyclohexane. In this conformation, all the bond angles are tetrahedral and all the CH bonds are adjacent carbon atoms are in staggered position. Figure 2.21. At the same time, there is no steric interference or dipole-dipole interaction between the non-bonded atoms. Thus, this conformation is essentially free of strain and has minimum energy. In other words, this is the most stable conformation of cyclohexane. Usual representation ball and stick model. Newman projection formula. Figure 2.21. Chair conformation of cyclohexane. Second, boat conformation. This is the second most important conformation of cyclohexane and is depicted in figure 2.22. As in the chair conformation, there is no angle strain in the boat conformation since all the bond angles in its are tetrahedral, but in boat conformation, the hydrogen on 4 of the carbon C2 and C3, C5 and C6 are ellipsed. As a result, there is a considerable torsional strain. Usual representation ball and stick model. Interfering flagpole hydrogen flagpole bonds. Newman projection. Figure 2.22. Boat conformation of cyclohexene. At the same time, the two hydrogen pointing towards each other at C1 and C4, known as flagpole hydrogens, are very close together, the distance between them being only 183 picometer or 1.83 angstrom, while the sum of their van der Waals radii is 250 picometer or 2.5 angstrom. This gives rise to van der Waals strain also in the molecule. Due to torsional and van der Waals strain in it, the bond conformation is naturally much less stable by 8.8 kilojoule per mole than the chair conformation. As such, only very few molecules of cyclohexane, only one in about 1000 at room temperature, exist in boat conformation. Other conformation. In addition to the chair and boat forms of cyclohexane, several other conformations are also possible as discussed below. Third, twist boat or skew boat conformation. Let us consider a model of the boat conformation of cyclohexane as shown in figure 2.23a. Suppose we hold C2 and C3 in one hand and C4 and C5 in the other hand and twist the molecule so that C3 and C6 go down while C2 and C5 come up. It will be noted that during this twisting, the flagpole hydrogens on C1 and C4 marked HA and HB in the figure move apart, and at the same time two hydrogens on C3 and C6 marked HC and HD in the figure beings to move closer together. In this way, we get another conformation called twist bot or skew bot conformation, in which the distance between HA and HB is equal to that between HC and HD. That is quite evident that in this conformation, the van der Waals strain between flagpole hydrogens is minimum. At the same time, the torsional strain on C2 and C3, C5 and C6 is also appreciably reduced. As such, the twist bot conformation is more stable than the bot conformation by about 6.7 kJ per mole, although it is slightly less stable than chair conformation by 23 kJ per mole. Figure 2.23 Twisting of bot conformation. Fourth, a half chair conformation. In between the chair conformation and twist bot conformation lies yet another conformation known as half chair conformation. Figure 2.24 it has both angle and torsional strain and has both 46 kJ per mole higher energy than chair form. In fact, representation merely a transition state conformation. Figure 2.24 half chair conformation. 2.25.1 Energy relationship between different conformation. The energy relationship between the different conformations of cyclohexane has been shown in figure 2.25. It may be pointed out that the energy difference between any two conformations is too small to permit their isolation. It is evident that the order of relative stabilities of different conformation of cyclohexane is chair conformation, then twist bot conformation, then bot conformation, then half chair conformation. 2.25.2 Equatorial and axial bond in cyclohexane. Since the chair conformation is the most preferred and the most important conformation of cyclohexane, let us examine it is a little more closely. Although the cyclohexane ring is not flat, we can imagine an average or general plane of the ring. Now, if we consider the position of various hydrogen atoms in the chair conformation, we find that there are two different kinds of hydrogen. 6 of the hydrogen marked He in figure 2.26 pointing side away along the general plane of a ring and are called equatorial hydrogens because they are situated along the general plane of equatorial belt of the molecule. The other 6 hydrogens marked Ha in two groups of 3 each lies above or below the general plane and points along an axis perpendicular to the ring. They are known as axial hydrogens. The bond by which an equatorial hydrogen is held is called an equatorial bond, and the bond by which an axial hydrogen is held is called an axial bond. There is one equatorial bond and one axial bond on each carbon in the chair conformation of cyclohexane. Figure 2.25 Energy relationship between the various conformation of cyclohexane. Figure 2.26 Equatorial and axial bonds in cyclohexane. It may be pointed out that the distance between hydrogen on an adjacent carbon atom in cyclohexane is 230 picometer, 2.3 angstrom, which is the same as in staggered ethane. However, axial hydrogens on the same side of the molecule are situated rather close together, even though they are linked to alternate carbon atom, but it may be noted that the distance between such hydrogen is also 230 picometer, 2.3 angstrom. It is interesting to note that axial and equatorial hydrogens in cyclohexane are interchange their positions. So this is because the chair conformations of cyclohexane is flexible and one chair conformation can change into another chair conformation by process known as ring inversion, ring flipping. As this happens, all hydrogen originally axial becomes equatorial and vice versa. But one chair conformation is perfectly equivalent to the other and they cannot be distinguished from each other. 2.25.3 Conformation of a mono-substituted cyclohexane derivatives. As the two bonds on each carbon of a cyclohexane ring are not equivalent in positions, a mono-substituted cyclohexane derivative should exist in two isomeric form according as the substituent group is in equatorial or axial position. Such equatorial and axial conformation of substituted cyclohexane are interconverted into each at room temperature by ring flipping, but they are not equivalent to each other in energy. The conformation having the substituent substituted in equatorial positions has slightly lesser energy than the other and is somewhat more stable. The reason for this can be understood by constructing these models. This can be seen from the models that substitution of an axial hydrogens by bigger atoms or groups leads to the considerably crowding between these substituents and the two axial hydrogens on the same side of the molecule. The interaction resulting from such crowding of axial atoms or groups is called 1,3-diaxial interaction. To illustrate the operations of such interactions, let us consider methyl cyclohexane. Figure 2.27 shows the two possible chair conformations of methyl cyclohexanes, one having the methyl group in an axial position, figure 2.27a, and the other having these groups in equatorial positions, figure 2.27b. Figure 2.27 the two possible chair conformations of methyl cyclohexane. It can be seen figure 2.27a that one of the hydrogens of axial methyl group on C1 is very close to the axial hydrogens on C3 and C5, but there is no such significant crowding when the methyl group is on equatorial position, figure 2.27b. In other words, axial methyl group is now crowding that the equatorial methyl. The resulting 1,3-diaxial interactions is responsible for the lesser stability of axial conformations than the equatorial conformations, the difference in their relative stability of the two being 7.5 kJ per mole. Since the difference of 7.5 kJ per mole of energy between the axial and equatorial conformations of methyl cyclohexane is due to 1,3-diaxial interaction between one methyl group and two hydrogen, it is reasonable to accept that 1,3-diaxial interaction between each axial hydrogen and methyl group leads to difference of 3.75 kJ per mole. This can enable us to predict the relative stabilities of the various conformations of substituted cycloalkanes having more than one methyl group. As stated above, the equatorial methyl cyclohexane and axial methyl cyclohexane can interconvert in each other readily and exist in equilibrium with each other. With a room temperature not included in the syllabus, 85% of the molecule of methyl cyclohexane and are those having axial methyl groups. This is apparently due to lesser energy or greater stability in case of equatorial methyl group. 2.26 Conversions of Fischer projection formula into Sahor's formula and Niemann projection formula. In conclusion of the discussion of stereochemistry of organic compounds, we may point out an interesting drawback of Fischer projection formula of diastereomers having two chiral carbon atoms. The Fischer projection formula of such compounds correspond to the lesser stability ellipsed conformations involving maximum crowding between the substituted group attached to the two chiral carbon atoms, but actually the molecules acquire the shape with corresponding to the staggered form in which the substituents are as far apart from each other as possible. Therefore, the best way of representing such molecules is to depict them in staggered form by means of Sahor's formula or Niemann projection formula as explained below. 2.26.1 Conversion of Fischer projection formula into Sahor's formula. This involves two steps as given below. First, write the Fischer projection formula and change it into its equivalent ellipse representation in terms of Sahor's formula. Second, rotation one of the chiral carbon atom by angle of 180 degree around the bond between the two chiral carbons to get the Sahor's representation of the staggered form. For example, let us convert 2s3r3-bromobutanol from Fischer projection formula to Sauer's formula. CH3CHOH CHBr CH3 2s3s3-bromobutanol but to all Fischer projection. Rotate C3 through 120 degree. CHBr CH3 CHOH CH3 Sauer's representation. 2.26.2 Conversion of a Fischer projection formula into Neumann projection formula. This also involves a similar procedure in which the Fischer projection formula is first translated into the equivalent ellipsed form in terms of Neumann projection formula. The latter is then changed into the staggered form by rotating through an angle of 180 degree around the bond between the two chiral carbons. For example, CH3CHOH CHBr CH3 2s3r3 bromobutol rotate C3 through 180 degree Neumann projection. Thank you.